money. And
Okay.
in fact, I was also invited at that time, but unfortunately, we could not join because we did not have enough people at that time. So, but
Mhm.
mostly IIT Hyderabad, IIT Madras, Samir Chennai, IISc, IIT Delhi. So it's a consortium project, and a testbed has been developed to demonstrate 5G for Indian conditions.
Yeah, yeah,
Yeah,
yeah.
so most of the hardware, I am in touch with those people group, and particularly the RF part I am interested, and
Yes,
Samir
yes.
Chennai is developing those RF.
Mhm.
So considering Indian condition, even the hardware, baseband, entire setup has been developed. So I can connect you to the main people in that.
Right, right. Yeah, yeah, sure, sir. And one of my friend is also contributing there. He's located in Bangalore, but supporting that project.
A
So
huge number of people are working. It was a massive project actually.
yes, 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 sir. Yeah, yeah. IIT Madras and this IIT Hyderabad, they are taking lead in this triple IIT Hyderabad.
And actually, this is the first time mm, both 3GPP and ITU, the standard bodies has
Right, right.
actually accepted the recommendation of this group. So
Okay,
this is
okay.
a big achievement.
Okay, okay, okay. Yeah. Okay, sir. Yeah, yeah, definitely. Yeah, it is big achievement. Yeah, from Indian
I
side. Yeah.
think I think 3GPP released 17. Some of these will come up, and ITU has already accepted.
Okay.
So a lot of works are going on.
Yeah, yeah. Even one of my friend, he is working in Ericsson, Sweden. They are also doing. They want some data from the farmers so that they can incorporate their problems when standardizing 5G for that particular use case. So this kind of activities are also help happening. That the companies, the big companies, they are talking to the actual users that would be using 5G.
No, no,
So that they can.
so 5G test cases has already been started in India,
Mhm.
and the Bharti Airtel is with Ericsson and Nokia.
Yeah.
Jio is developing their own, and also Vodafone. They are also with some of the telecom
No, Jio is
and
working with Samsung, sir. Jio is also
Samsung.
working with Samsung also
Yeah.
on Open RAN and other
So,
things. Yeah.
so some successful text runs
Absolutely.
have already been done at the outskirts of Delhi, I think NCR region. Recently, Airtel has tested outskirts of Calcutta. Pune, some tests have taken place.
Yes, sir.
And the newspaper report says that now 13 cities are ready for actually roll out 5G in 13
Okay.
locations.
Yeah, yeah. Yeah, even Meenakshi ma'am is also here. So we were in discussion with Meenakshi ma'am. So hello, good morning, ma'am.
Yeah, just give me. Hello.
Yes, actually, it is very interesting to hear about 5G test beds. I'm sure that it is not very much known, but View is also starting the testing now. We
Yeah,
have one set up in IIT Roorkee and one is in IIT Mumbai.
right,
So
right.
yeah, they are supported by Samsung mostly, but they are trying to replace most of the components with indigenized components. So we
Right.
hope that we can make a mark there also.
Yeah, sure, ma'am. Yeah, okay, okay.
Acha,
Okay.
acha, acha. I'm delivering a talk. Can you call me later?
5G things keep
My mobile
getting
number,
postponed.
please note down.
From 2020, I'm hearing that this year it will be
Acha, acha.
launched. Now I am hearing that this year it will
মোটামুটি
be
আমি
launched in
সিসি
June. So
সিসিতে
we
এলাই
hope
হলো
that we will
কম্পিউটার
be seeing
কমিউনিকেশন
something.
সেন্টারে হ্যাঁ
Yeah, ma'am. Yeah, it has been delayed. That is the thing. But yeah,
মাইনে
definitely this year something should happen. Concrete
So,
should happen. Yeah.
so I think
মাইনে
I
this
agree
year,
with.
we are
1 month.
only expecting auctions. So I think the implementation will start sometime early next year because
Right, right.
people will need to gear up and align their technical as well business cases also with that. And so Professor Bhattacharya, since we are on the topic of 5G, just let me share with you. I'm also active, proactive member of the 5G high level forum under DOT. So I've been
Oh,
contributing very proactively on the application layer standards and also as chairman, founding chairman of the BIS LIT 28, which is on smart infrastructure and smart city standards. So there we are also looking at the different use cases and how we can, come up with a structured approach to migration to 5G rather than disruptive approach. When a lot of use cases 4G itself is good enough. But when 5G comes, people are going to push it. All the service providers, they say, well, no, you should go for 5G. But will that really make a business case for every use case? So those are kind of studies we have already done. And I'm also a proactive contributor in IEEE 5G World Forum, where we have been talking on a lot of interesting aspects. So anything on 5G, I'll be more than happy to share my perspective for last 5-7 years that I've been working in there. But I'm more on the application side, use cases side, and system architecture level rather than on the core.
Kushalendra is from industry only. So he is representing industry side, and in today's actually workshop, they will be conducting the hands-on.
Okay,
So,
great.
Kushalendra ji, you can connect with Kishore ji also.
Yeah, sure. Sir, we have already spoken once, so I will continue to talk to him further. Yeah, thanks, sir.
Thank you.
So Firoza, can we go ahead? We are already 17 minutes behind the schedule.
Yes, sir. Sir, Professor Vineet Sahula, sir, is not well, so he won't be joining the session today, sir. So with your permission, sir, shall we start?
Yeah, please.
Thank you, sir. Good morning, all. On behalf of all the organizing E&ICT academies, I welcome you all in this 2 weeks online joint faculty development program on Internet of Things, Smart Systems, to be conducted from 14 to 25th Feb, and which is jointly organized by E&ICT academies at NIT Patna, MNIT Jaipur, IIT Roorkee, IITDM Jabalpur, and IIT Kanpur. We have with us the principal coordinator of this program, Professor Ratnajit Bhattacharjee, sir. So I request sir to please say a few words in this inaugural session and motivate the participants. Over to you, sir.
Thank you, Aditi. So this platform actually also gives us to interact with many of our colleagues. I could see Dr. Meenakshi there. So this EICT academies together, as you know, we conduct this, I was telling, these faculty development programs to keep the faculty members updated about the latest happening in academics as well also in the industry. And we want this to indirectly go to the courses being taught by the faculty members in their respective institute. So the student indirectly, they come to know about what is happening, because many a time our curricula in the institutes, they do not change that very fast, keeping in pace with the changes in the industry. So these FDPs are very, very useful tools in keeping pace with this change. And E&ICT academies together for last 6 years, we have conducted several such courses. This is one such initiative. And IoT, as you know, and as it will be discussed, is coming in a big way, and it is going to influence almost and touch upon almost every activities. And therefore, we also gradually start getting adapted to how and what technological changes IoT is bringing. Just last week, I was delivering a similar talk in IIIT Guwahati. They are also conducting, in fact, it is going on a similar workshop on IoT. And some of the participants asked that whenever we attend IoT workshops, people always talk about application. What are the research components? Definitely, the faculty members would like to know more about the research components as well, along with the application. So I should tell that for this course, we have taken every care that along with the application, for us, IoT is not only an application. There are also lot of scopes for academic research, and we have taken care to choose the topics which will provide a lot of such opportunities and many research gaps will be highlighted by the experts while delivering the talks. So I would request my faculty colleagues attending this program to interact with the experts. We have experts from industry as well as academia, not only on the application part of IoT, but also possible research opportunities in this domain. I have lecture scheduled after that. I will not continue further. I just thank all my colleagues who has taken actually a lot of pain in forming this and spend their time in forming this program. And I'm thankful to large pool of colleagues from different institutes across the country who have shown actually interest in registering this program and interacting with us. I hope all our initiative becomes successful. With this, I hand over the platform back to you, Aditi.
Thank you, sir. Now I would request the Principal Investigator of ICT Academy IIT Guwahati, Dr. Gaurav Trivedi, sir, to please address the participants in this inaugural session. Over to you, sir.
Yeah, thank you, Aditi. Thank you, Ratnesh, sir. All my colleagues from different institutes and all the participants, a very good morning to you. We welcome you in this particular joint FDP, which is being hosted by, being hosted jointly by different ICT academies pan India. As Professor Bhattacharya have told that this is the impact and the necessities of this particular course is or this particular course. I do agree with him, and I'm to say not only I just want to just add that not only the application part, the research domain in this in the IoT segment is really very large. That spans from ultra low power to many other you can say many other such areas. So this is precisely not only the application, but the research scope precisely is used. I wish everybody a very good luck for this course, and I believe that you will enjoy this course. Stay safe and healthy. Thank you. And Aditi, you can further continue and invite other colleagues for the interaction. Thank you.
Thank you, sir. So now I would request Professor Vineet Sahula, sir, Chief Investigator of MNIT Jaipur ICT Academy, to please address the participants in this inaugural session. Over to you, sir.
Yeah, thank you, Aditi. And very good morning, Professor Bhattacharya, Professor Gaurav, Professor Manhas, Professor Lav Bhargav, Professor Bharat, my other faculty colleagues at organizing academies, and participating faculty members and students. I think this journey of academy started about more than 5 years ago, which has taken shape of delivering very robust programs from the point of view of the contents, the speakers, and of course joining participants. So it is all depends on how we get the participation that way. Regarding the research gaps, I slightly work into this field. If you are looking for many of those things, they are, as Gaurav indicated, it's a low energy edge devices, low energy IoT devices. And more importantly, now the computation is shifting to edge side. So it is edge intelligence, which is much more on the forefront, getting impact of your artificial intelligence as well as the deployment of a large number of these IoT and edge devices. So I will just congratulate Dr. Bhattacharya, Dr. Gaurav for weaving up such a nice program here. I would like to attend few of these sessions also.
Thank you, sir. Now I would invite the Chief Investigator of ICT Academy IIT Roorkee, Professor Sanjeev Manhas, sir, to please kindly address the participants in this inaugural session. Over to you, sir.
Sir, your voice is not coming. You have to unmute.
Okay. Yeah.
Thank you.
So very good morning to all the PIs and all the experts present for this program. And good morning to all the students, and good morning particularly also to Professor Atarjit Bhattacharya and all of my colleagues at ICT Academies. And this is yet another program run through this concept of countrywide classroom, where we run quality programs in the latest areas which require training and upskillings of faculty members and research scholars and whoever else is interested in these programs to ensure that the knowledge and the training is imparted in the latest areas where there is a need of talent and manpower. And we also hope by doing such program is that after having done programs like this, the the candidates or the faculty members who attend these programs are able to translate this into either a course module or a project in their own classrooms, labs, or maybe in their sort of work lives. We do hope by doing such programs will have a multiplier effect where ultimately the end beneficiaries will be the students of the institutions or the working professionals are able to develop required skills and knowledge to make them more employable, to make them more industry ready, because that is what fundamentally or basically this whole initiative by MIT is all about, to generate manpower or to train the manpower or to bring out the manpower from the institutions which are industry ready, which can be absorbed by industry. So IoT being a very important topic, is almost like a backbone of AI, because it is IoT which generates the data for AI, and working with IoT, understanding the fundamentals as well as the networking and other concepts involved in IoT is very important for electronics engineers to know and to adapt and to apply this knowledge for various practical applications. So this course is very well designed to deliver a kind of very uh, balanced material, both in terms of fundamentals, but also a lot of practical applications and hands-on projects. So I'm sure that all of you, the participants, will enjoy this program and will learn something which you can then put in practice in your own professional work. And I wish you all the very best and very happy learning. And I hope that you will be able to join again sometime in one of another of our programs. There are many other different programs in addition to this which are coming up of similar nature or something which are also of similar importance. So please do take a look at those programs also. You would have seen our brochure, and I request you to also recommend any of other your friends, colleagues who you think might benefit from this program. So with this, again, I would like to thank you all and wish you all the best. Thank you.
Thank you, sir. Next, I would like to invite the Chief Investigator of ICT Academy, NIT Patna, Dr. Bharat Gupta, sir, to kindly address the participants in this inaugural session. Over to you, sir.
Yeah, thank you, Aditi. First of all, a very good morning to all the chief investigators present here and all the experts. And on behalf of NICT Academies, all the academies, I would like to invite all the participants to be a part of this program on IoT and its application, that is smart system. So as all the uh, speakers have already said about that, the importance and the things what we are doing in the academy. I would just especially mention about this course that this IoT we can also say is one of the backbone for the industry 4.0, and it is initiated based on that. And in this program, we we have tried to touch upon each and every aspect of the starting from embedded system communication protocols, IoT protocols, the security aspects, edge computing, cloud computing, and lot of applications in almost each and every domain. Going towards healthcare, smart farming, and the other applications. So this course will enlighten you the all the aspects uh, for your research as well as for your academia, and that will opens the gate for the newcomers that what are the possible uh, ways that we can start their research. We can start developing the IoT systems. How we can use it in different, much more rigorous applications. And as Manas sir and the Saula sir has already told that this is the backbone of the AI. It generates a lot of data, and we can do the analysis at the edge as well as in the cloud part. Both parts we can do that. So I hope this participants will really be benefited with this course. And and with these words, I just welcome all of you, all the participants, and I would like to congratulate Ratnesh Bhattacharya sir for the mapping this whole new course. I mean, it's a new way, including the all aspects at one platform. And and I would like to say all the best to all the participants for the next 10 days. And I hope they will do justice to their learnings and utilize it future endeavors. So thank you so much from my side.
Thank you, sir. So next, I would request the Joint Principal Coordinator from IIT Roorkee, Dr. Meenakshi Rawat, ma'am, to kindly address the participants in this inaugural session. Over to you, ma'am.
Thank you very much. I really appreciate that these kind of courses, they keep happening. So this is the need of the country that, we do things practically also. And when I see the content, it has been very nicely arranged. So we start with the theory, but we do lots of hands-on practice and which engages the audience. So the application wise, they have tried to cover so many things: smart homes, wearable and IoTs, intelligent transport, healthcare, smart farming. So nicely packaged program is being offered here. So I really appreciate that it is being organized under this gist of all these academies. And I invite and welcome all the participants. And I hope that by the end of this course, you will have touched upon all the main aspects of the IoT. So welcome all of you. I will not take much time here. Thank you very much.
Thank you, ma'am. Next, I would like to invite the Joint Principal Coordinator from MNIT Jaipur, Professor Lava Bhargava, sir, to please address the participants in this inaugural session. Over to you, sir.
Hello, everyone. Thank you. In interest of time, I will be very short. So, as we have seen earlier, we were organizing courses individually, but the day we shifted to this common platform for all the academies, the response has been very good. Looking to the COVID situation, we have had courses mainly in terms of online, completely online. But I think with the situation improving, next time maybe we can have something the same mode, but those who want to come to the various academies and do practical sessions from there, that would provide another way of operating. So thank you and welcome to the participants for this workshop.
Thank you, sir. So next, I would like to invite the Joint Principal Coordinator from NIT Patna, Dr. Suyal Namasudra, sir, to kindly address the participants in this inaugural session. Over to you, sir.
Thank you. So first of all, good morning to all the panel members present here in this inaugural session, as well as all the speakers and participants and other faculty members. It gives me a great pleasure to welcome you to this 2 weeks joint online faculty development program on IoT and application smart system. So other faculty members and principal coordinators have already told so much. So this course has been designed so that we could get some all the information from the basic to the application. So like application in the area of farming and like smart cities, then security concern, all the concept would be covered in this lecture. So there would be 20 hours lecture and 20 hours hands-on. So I would request to all the participants to attend all the session to have a good knowledge and to be very proficient in this course. And this course would be very good. In fact, the syllabus and the topics are very emerging. And I would again like to express the entire organizing team of IIT Guwahati. They have been working a lot since starting, as well as other academies, and our director sir from IIT Patna for allowing us to participate in this FDP, and other participants. So without participants, it could not have been possible to organize such kind of FDP. So I hope that everyone would take the results of this FDP to apply the applications of IoT in different area. And I wish that it would be a great learning journey in the coming days. So thank you. Thanks a lot.
Thank you, sir. So next, I would like to invite the Joint Principal Coordinator from IITDM Jabalpur, Dr. Neelam Dayal, ma'am, to kindly address the participants in this inaugural session. Over to you, ma'am.
So good morning, all the panelists and all the attendees. First of all, I'd like to congratulate the organizing committee of IIT Guwahati to prepare such a great content for this IoT and applications FDP. It is basically amalgamation of lot of theory sessions as well as the hands-on sessions, and the content is so rich that has attracted so many attendees and participants from all over the country. So first of all, congratulations on that. And definitely this content will help all the participants to update their knowledge domain, and indirectly helping their students to develop the skill set required for such cutting edge technologies. And also it will help them identify the existing research gap in the domain. So definitely it is going to help them a lot. And I hope all the participants will be benefited out of this program. And best wishes, I want to convey my best wishes to all the participants and organizing committee for this upcoming FDP. So thank you.
Thank you, ma'am. So next, I would like to invite one of our keynote speaker, Dr. Momita Patra, ma'am, from IIT Guwahati, to kindly address the participants in this inaugural session.
Hello, am I audible?
Yes, ma'am, you're audible.
Yeah. Okay, thank you for inviting me, and thank you for giving me the chance to talk in the inaugural session. And first of all, I welcome all the participants here. And so in this particular event, what I'm going to do is what I am going to take as a particular lecture. So I will just talk about a little bit about that. So I will be talking about Internet of Vehicles and edge computing. And because, you know, autonomous vehicles and intelligent transportation systems has become a very lucrative research area now. So I am hoping that with the lecture that I will be giving, it will give you some perspective on, you know, how networks, how in terms of wireless networks or how in terms of networking, we have certain challenges, some security challenges, some other issues that we face, and some issues with edge computing also. And I hope that it will help you out a lot. Okay, so this is all from my side. I will not take much time. So thank you. Thank you all. Yeah.
Thank you, ma'am. So next, I would like to invite our another keynote speaker from industry, Mr. Narang Kishore sir, to kindly address the participants in this inaugural session. Over to you, sir.
So good morning, one and all. I think it's a great opportunity and to share my personal perspective, which I've learned in last more than 4 decades as a design engineer with the wider community. And I think researchers and the faculty are in fact the real drivers of you can say any nation's future, the way whichever direction we want to take. The way I always talk is that rather than teaching 50 students this thing, if I am able to teach the same thing or train the same thing for 5 faculty members, I think they will be able to teach 50 students every year. So I think this is very, very relevant and very pertinent. Coming from talking about the IoT and technology, I think it's an evolving technology which started as a science fiction, this thing 2 decades back, but today it has become more pervasive and become the kind of part of our life. We don't even question how the IoT functions and it helps in different aspects of our life. So I think industry perspective and the daily use cases perspective is very, very important. And then there is another aspect that I'll be talking in this time will be standardization. But I think beyond standardization, what is more important for Indian researchers, designers, faculty, and rather than engineers across the nation is how to design a most rugged, reliable, and valid IoT product, system, or solution. I think this is the focus area which we are missing in India. Our engineers do not understand how to design a comprehensively rugged, reliable, world-class IoT products, systems, or solutions. So I think this is one of the area we need to focus simply beyond learning about the overarching principles, applications, concepts, and research. We are pretty strong in research, but how about design? The Make in India initiative will be only possible if we have the right kind of competence to design all the IoT products or any other kind of products and system solution that we are looking at as a country. To become part of the global value chain, it is crucial we focus along with the research to design of the products, system and solutions, and what kind of extra skill sets are needed to convert the theoretical learnings that we do in our academic stages of the career, to convert them into world-class product system solution that the society, the industry, the business, and in all domains, different use cases are there. I'll not get into those domains, but I think industry and infrastructure, these are 2 major domains where I think IoT has found a lot of use cases. And as a nation, we could look at a lot of interesting use cases and the focus to serve the society. But I think I'll stop with this, but I think I'll re-emphasize the importance of standardization and design competence and design capabilities and temperament for IoT product system solutions. So I'm not touching on standardization, which I'll be touching basically dealing with in details on my talk on the 24th. Thank you very much.
Thank you, sir. Thank you for your motivational words. So next, I would like to invite the keynote speaker, Mr. Kaushalendu Singh Sisodia, sir, from IoT Academy, who will be taking the maximum hands-on session in this program. Over to you, sir.
Okay, thank you, ma'am. So good morning, everyone. Thanks to Ratanji sir and all PIs and all the participants. So I would like to mention already all the things have been very much articulated by all the speakers. So I would like to summarize that since IoT is about the technology innovation as well as affordability of the solutions. So until unless the academia is not coming up with the innovations, it would be difficult industries to implement in a commercial way. So it is very important that academia work for the affordability, and because this is having a vast penetration in all areas in our life. So until unless we have a cheaper solution, affordable, it would be difficult to wide adaptability of IoT. So academia has a very big role to play into this thing. So with this, I would like to conclude myself, and we have been given responsibility to deliver the hands-on sessions. So we would try to give the best justice to the expectations that our audiences and the managing committee has decided to give the responsibility to us. So with this, I would like to conclude my words. Thank you, everyone.
Thank you, sir. Thank you for your motivational words. So next, I would like to invite Mr. Jitesh Kumar, sir, from IoT Academy to kindly address the participants in this inaugural session.
So good morning, everyone. Am I audible?
Yes, sir, you're audible, sir.
So thank you, the organizing committee, for giving us the opportunity to deliver the hands-on session on this FDP, joint FDP. So in this FDP, we will try to cover the maximum application of the IoT in recent research topic. So you will definitely enjoy the hands-on session. So welcome to all the participants and thank you, organizing committee. Thank you.
Thank you, sir. So with this, we come to an end to this inaugural session of this 2-week online faculty development program on Internet of Things. So we request, thank you all for joining in this inaugural session and motivating us for conducting this course. Thank you all. So shortly we will start with the first lecture on overview of IoT, evolution and technologies used in IoT, which will be conducted by Professor Ratnajit Bhattacharya sir from IIT Guwahati. Hello. Ratnajit sir, we have made you the presenter, sir.
Can I share my screen and start?
Yes, sir. Yes, sir. Sir, we have given you the presenter, right, sir?
Oh, great, great. Okay. Thank you. Is my screen visible?
Yes, sir. Your screen is visible, sir.
Just give me 1 second. I am going full screen. So welcome to this very first session. We are running slightly behind the schedule. And this first session is actually to provide an overview of IoT, talk about the evolution of technologies used in IoT, and provide a generic platform where my other colleagues, they will take into greater detail. So in this session, I'll touch upon many topics, but mostly I'll be talking about the titles of the topics, not going into much detail, which will be expanded in later sessions. So as it is mentioned that IoT concepts are just 2 decades old. In fact, it was 1999 essentially, and it emerged from RFID community. The terminology IoT was actually framed, but it became so popular that by 2014 or 15, we have a IEEE journal of Internet of Things. So it grew that fast. So I'll go to those. So Internet of Things is the network of physical objects that contain embedded technology to communicate and sense or interact with the internal states of external environment. So this is the definition I have taken from the reference given here. And if you look at how it is blowing, this technology has grown almost exponentially. You can see that Internet of Thing and non-Internet of Thing active devices connected worldwide. So by 2025, it is expected to be 30 billion. Right now we are here, 2022 already it is 16 billion, double the population of the earth. So these are the huge number of devices and that are going to be connected to the internet. And then you will say, what's big in it? So this number itself is mind-blowing, and you require new technological and innovation to accommodate this large number of devices. And also, as mentioned by my previous colleagues during the inaugural, the huge amount of data they are going to generate. Those data will need to be analyzed. So side by side, you require development in AI, machine learning, storage, whatnot. So with this in mind, let me just quickly go through the plan of the presentation of this particular session. I will try to wind up as early as possible and make up for some of the time. So we'll try to go for a formal definition of IoT, identify some application areas in IoT, then sensor node block diagram and sensor types, common IoT application development platforms, what are used in industry. Then I will talk about the basic IoT architecture. Communication models for IoT, I'll just touch upon in this talk. We have separate session on that where we will go into detail. Similarly, radio solution for IoT. And then above the physical layer sits the protocol stack in the higher layer, which do the functioning for IoT. So a brief idea about the IoT protocol stacks, which will be expanded later by my colleague. And some IoT applications, smart city, industrial, agricultural, and geohazards. Mr. Kishore has mentioned about smart city and industrial, and I feel in the Indian context, other two very important application areas for IoT is agriculture and mitigating geohazards. Lot of scopes, lot of interdisciplinary research activities, and also coming up with system level solutions are possible. And then I'll conclude this session. So Aditi, you can hear me clearly and the slides are visible. No issues.
Yes, sir. The slides are visible, sir, and you're audible also, sir.
Thanks. So I will request the participants to in between, I will ask something and please respond to it so that I am aware that you are listening to me. I am not seeing you. This is the main disadvantage of this mode. I am talking before a computer and I want to make sure that you participate fully and you give your full attention. So time to time I will be probing. So here we go for a formal definition of IoT. So it is an ecosystem of connected physical objects that are accessible through internet. Now, what is this thing in IoT? Internet of Things. So what do you mean by thing? In the context of IoT, is an entity or physical object that has unique identifier. That means it has some address. And when it is connected to internet, it will have to have some internet address. an embedded system, and ability to transfer data over network. So an embedded system, it will have a microcontroller, a processor, some other form, and transfer data means it will have the capability of communicating. So when you have all these characteristics present in a physical device, that it has a unique identifier, it has an embedded system, it has the ability to transfer data over a network, then you call it is a thing. And in the Internet of Things, all the things are being connected to an internet can put into three categories. Things that collect information and then send it, things that receive information and act on it, and things they do the both. So in the first case, the things they are doing only data gathering, but there are certain applications like home automation and all, a thing need to do some action also, take some action also. So execute some commands also. So the things that receive information and then act on it, and there are things which can do both. So already some application areas has been mentioned. The application areas are really large. I've just listed few. So as I told, prediction of natural calamities and disaster, combining IoT, AI, ML is very, very important for a country like us. Industrial application, of course, is at the center stage. Smart home, healthcare and medical, particularly today we are getting a lot of wearable devices, flexible electronics, and medical application and wearables. These are another area. And I feel one of the very important area for a country like India, where IoT will find lot of solution, is agriculture. And intelligent transportation systems. Most of our cities, particularly metro cities, are congested, and traffic management becomes a very, very vital issue. Overall, smart cities, smart environment, smart water, some smart healthcare, smart transportation, we'll come to that. Then smart grid is something what is again coming away, and smart metering and monitoring, and smart security solutions. So these are some of the areas where IoT can find application. Just let us try to develop some very basic understanding without going into the detail, which will be covered in detail by my colleague in later specialized lectures. So if you look at a IoT sensor, it will have, as we have mentioned, the capability of sensing. It will have some data converter, because analog and digital you need to switch. It will have some storage units for data storage. It will have a microcontroller or a processor inside. And more importantly, it will be having a connectivity. So my area being wireless communication, I will talk little bit more on the connectivity. And we have two lectures scheduled on this IoT communication protocol. So one of the lectures immediately after this introductory talk, I will continue and cover some of the communication related topics. So if you look at the broad categories of IoT sensors, so IoT is present everywhere, and we have motion, movement, velocity, acceleration, rotation, position, orientation, proximity, location. So these are the parameters you need to sense, integrate. The kits that we get normally, they do not have all these sensors, maybe having one or two sensors. But if you want to develop a full-fledged IoT solution for a particular application, you need to integrate many other sensors. And these sensors need to be calibrated, and particularly when you are going for a prediction and other things, these are to be very, very accurate. In some cases, these sensors will be placed in very difficult places where you won't be able to monitor the health of the sensors after they are installed. So these are very, very robust sensors are developed. So these are some of the practical engineering challenges. Environment is temperature, humidity, acoustic, radiation, gas, weather, chemical. Then biosensors, blood, tissue, and other pressure, density, deformation, flow, strain, corrosion. So you can see a wide variety of sensors are there, and IoT platforms need to integrate those sensors. Today afternoon, there is a full-fledged 2 hours of dedicated talks will be there on the sensors. So some common development platforms which we use in laboratories and other places, for example, Arduino boards, then Raspberry Pis, Picom IoT boards, Intel boards. So these are very popular boards which are used for developing IoT application, small scale. This is a technical specification of the board. Now coming to the architecture of IoT. Usually a layered architecture we follow. So the basic IoT architecture was a 3-layer architecture: sensing, networking, and data communication. And next is application. So this is the basic 3-layer architecture. And this sensing is also called the perception layer. Networking and data communication is also called the network layer. And applications, definitely it is the application layer. Now this is the basic architecture. Over the time, this architecture has also evolved, and now what we call is a 5-layer architecture. It is perception, transport, processing, application, and business. This is very, very important business layer, business model, because IoT will have lot of impact on the industry. And how do you, Mr. Kishore was telling about the case studies, how you build. So this is very, very important. And perception layer, of course, the physical objects, RFID, barcode, sensors, network layer, secure transmission. Now, many technological solutions are possible. We will discuss to some detail here. And middleware layer is the information processing, the computing, service management, database, and application layer, smart application management. So this is the way IoT is looked into nowadays. Is it all right, Aditi? You can hear me?
Yes, sir, we can hear you, sir.
Yeah. So how about the questions? We take later at a time, or in between also I can respond to the questions. Please tell me if there are questions. Huh?
Okay, sir. Okay, sir.
So let us come to the communication model for IoT. Communication model, what we mean is what are the different ways the communication. I'll come to the technologies later. what are the different forms of communication that we encounter when we go for IoT type of an environment. So very 4 common communication models or forms of communications are used by IoT device. So this is very, very distinctive. IoT requires device to device communication. Unlike your cellular or this type of communication where you are always getting connected through a base station, in IoT environment, we need one device capable of talking to another device directly. And there are, of course, a lot of communication protocols have already been developed. When you do a Bluetooth type of transfer from one mobile to the other, you do not go through the base station. You talk directly with each other. So device to device communication is one very typical characteristics. Then another is device to cloud communication. Nowadays, most of the information that we send reside on the cloud, and your device gathering information need to transmit this information to the cloud. So device to cloud communication is very important. Device to gateway communication, there are intermediaries, gateways, and how do you do the ultimately they will connect you to the device to the internet. So device to gateway is also another important form of communication, and back-end data sharing. So usually IoT communication models will fall in any one of these 4 categories. I'm giving the references that I have consulted in building those slides, so you may look into further details. So device to device communication represents 2 or more devices that directly connect and communicate between one another. So this is very, very important characteristics, as I already mentioned. And today, actually, the communications are also characterized by M2M or machine to machine communication, where at the both ends of the communication link, it is the machine. Already Momita talked about V2X. There you will find a lot of such applications. And most commonly used protocols are Bluetooth, Z-Wave, Zigbee. These are short distance communication. And this model is commonly used in home automation system to transfer small data packets. So in a device to cloud communication model, IoT device connects directly to an internet cloud service exchange data and control message traffic. It uses existing communication mechanism like traditional wired Ethernet or Wi-Fi connection to establish a connection between the device and an IP network, which ultimately connects to the cloud service. Device to gateway, the IoT device connects to an intermediary device to access the cloud service, and application software operating on a local gateway device like a smartphone or a hub that acts as an intermediary. For example, this personal fitness tracker, you put these devices on your body, and first they talk to your mobile phone, smartphone, and applications are there which actually ultimately transfer the data to the cloud. And finally, back-end data sharing model refers to communication architecture that enable user to export and analyze smart object data from a cloud service in combination with data from other sources. So if we look at the connectivity in IoT, the challenge now here, the research and design challenge, both are there in connecting multiple devices across distributed location in a cost and energy efficient manner. So either you propose some new protocol or you think of a network configuration where you can connect the devices in a cost and energy efficient manner. And energy efficiency, I tell you, is going to play a very, very critical role in future also. And the battery lifetime, increasing the battery lifetime of these devices even up to 10 years, this is what is targeted. Wirelessly charging those device power sources are also coming up. So there are a lot of development. Devices are expected to run on a single cell for years without manual intervention. And the volume of data transmitted in M2 is much less than voice or video call. So these are some of the characteristics. When it is IoT type communication, the amount of data that you are transmitting in majority of the cases is not very high, because the IoT devices will send the data only when there is some change is actually observed. So to keeping the volume of data less and sending it in an energy efficient manner constitute both research challenge and system design challenge. The transceiver sleeps most of the times and wake up only in transmit data. I've seen recently many AI based or machine learning based protocols have been proposed to actually control this sleep and wake up time in an optimal manner, saving a lot of energy. So this is about the general requirement. Now, what are the radio solutions that are currently available for IoT? Already developed radio solutions and system design can be carried out around this. So we usually categorize them in long range solutions, in medium range solutions, and short range solutions. Cellular network, of course, it is there. You can connect devices, but cellular network, many a time, it becomes very costly. Another evolving connection technologies or connectivity is low power wide area networks, LP1 technologies. And this is, there are many competing technologies are there. LoRa, for example, Sigfox, Ingenu, their technologies RPMA or random phase multiple access, Moiety, Talensa, and all. Similarly, our cellular system, they also provide NB-IoT, then ECGSM, LTEM. So these solutions which can be used for IoT. And if you want to have very long distance coverage, then satellite communication is also another option. When it comes to medium range, where actually you want to connect maybe within a building or some home environment, Zigbee, Thread, Z-Wave, Wi-Fi, Li-Fi, these are some of the technologies available. And short range, of course, Bluetooth, BLE, RFID, infrared. So these technologies are developed for short range communication scenarios. We have a complete session on communication technologies. In fact, 2 lectures where we will try to understand some of these technologies in more detail. Just here I make a comparison that actually will give you some idea. For example, if you go for a RFID type solution or a Bluetooth type solution, you can achieve higher data rate but at a shorter range. So we have the x-axis giving you the range, the y-axis giving you the data rate, and the third parameter here is the color, which gives you the change in color, gives you the cost. So Bluetooth is a relatively low cost technology which will give you moderate to high data rates for a short distances. Whereas if you go for a cellular solution, 5G, LTE, you can achieve much higher data rates of 100 Mbps over a large distance of about 10 kilometers, but the cost will be very, very high. This is the upcoming area, unlicensed LP1, LoRa, Sigfox, and other technologies, which give you a data rate, low data rate solution, but can cover a very, very long range. So how do you design your system taking into account the capabilities of existing technologies is very, very important. And this is what in the inaugural session, Mr. Kishore has actually mentioned the designing system taking into account various factors. That capability we should have. So I was talking about the physical connectivity or communication protocols. Now, if we come to the slightly higher order protocols stack, so at the this is the basic physical layer protocols, either use IEEE 802.3 or 802.15 or others. And then you have the internet protocol version 4 and version 6, 6 LoWPAN. So these protocol stacks are there. Then you have TCP and UDP. And then you have the application protocols which have been developed specifically supporting IoT applications. So these are MQTT, COAP, MQP, HTTP can also be used. So MQTT is message queuing telemetry transport protocol. COAP is constant application protocol, and AMQP is advanced message queuing protocol. So these protocols will be discussed in detail in the subsequent sessions by my colleagues when we discuss the IoT protocol. I just made a mention of it. Now coming back to the application, IoT application, first, of course, one major solution is IoT is going to give us the smart city solution. And cities can become smart using combination of Internet of Things with sensors collecting data and AI implementing insights obtained from the data, as was mentioned by some of our colleagues during the inauguration session. So this is very important. IoT and AI, they go hand in hand. And what areas we can actually develop IoT based applications, traffic management, public transport, parking. Parking is a major issue, healthcare, air pollution monitoring and control. Like you know what happens to our cities, Delhi and all. Many a time pollution levels become very, very high, and water management. This is another major area in most of our cities. Drinking water is a major issue, and lot of water get wasted either, and in some of the cases, like in Guwahati city, we are sitting at the bank of mighty river Brahmaputra, but you ask people living in Guwahati city, many of them has drinking water problem. So this is where the technology should chip in and provide solution. The buildings, waste management, this is another major area, because the dumping of waste and their management, and nowadays of course many municipalities are coming up with smart vehicles having these tags and all. They can be tagged from where they are collecting garbages, and the operation of these things can be optimized. There quite a good number of pilot project has already been made based on that. Natural disaster management, as I told, I will elaborate little bit on that. Infrastructure. When it comes to industrial application of IoT, which is one of the major driver, and people are talking of Industry 4, automated and remote equipment management, predictive maintenance, automated monitoring of inventory, supply chain optimization, quality control, smart automotive manufacturing, improvement of plant safety, robotics, packaging. So these are different areas in industrial environment where this IoT is going to impact. As I told in the very beginning, that there will be a complete session on smart farming. Just going into the summary, agriculture is an area on which our country is very much dependent, and there are issues regarding just despite having just 1/3 of the gross cropped area under irrigation, agriculture consumes 89% of our extracted groundwater. So these are some of the major issues, and according to some reports, more than 1/3 of India's population lived in water stress, and India is one of the 17 countries facing extremely high water stress. So you can see that precise and adaptive irrigation system is the need of the hour, and it can be realized employing IoT and machine learning. So several solutions have been proposed. The details will be discussed in a special session. Just to tell, you need to integrate it, weather data, then machine learning system, communication and control network, irrigation pump, actuators, and also sensors taking the measurements on soil temperature, soil moisture, air temperature, humidity. All these factors decides whether the land need to be irrigated or not. Similarly, machine learning and IoT based soil health monitoring system, these are also proposed. And wireless sensor network and IoT for data collection, machine learning and deep learning for model development and prediction. So in combination, IoT based soil health monitoring system can be developed. I think in the smart farming session, these things will be dealt in detail. So you can see the scope of IoT and AI. One is, of course, big data analytics, maintaining the production, then crop production, farm management, data analysis, sensing and monitoring. This will be done by IoT, and then communication protocol and physical implementation, that also along with the security management will give complete AI IoT platform for smart farming. Another area where IoT may find a lot of application in coming years, we have already proposed a solution. Almost 18 institute together, we have proposed for a center for geohazards, particularly our coastal areas and Himalayan, the states situated in the foothills of Himalayas. They experience different form of hazards, flooding, thunderstorm, then landslide. So IoT will definitely have a lot of scope in developing geohazard monitoring, early warning system, and actually informing the command and rescue system. So if I come to the challenges faced by IoT in general, of course, the scalability is an issue. Security concerns are issues. So we have kept one full session on IoT security, technical requirements, as we have talked about technological standardization, and of course, we have a full session on standardization towards the end of this course. Software complexity, meeting customer expectation, and overcoming connectivity issues. IoT for its operation need connectivity, and that is very, very important, that connectivity also should grow. So for this session, if some final comments are to achieve higher energy efficiency, the IoT network with limited bandwidth and low transmit power, to provide low latency IoT services in an energy efficient manner. So this is very, very important, as more real life application or real time application you try to do using IoT, the latency or the delay that is produced by the network has to go down, and there is a lot of scopes of research. Developing energy efficient computing platform for IoT. Every time we are talking of application of AI machine learning in IoT systems, but those things requires a lot of computation. First of all, the devices that we use for IoT at present, embedded systems, they do not have very high computing capabilities, but people are trying to increase the computational capability toward the periphery of the network, and that's where the edge computing possibly will be discussed in detail. But whatever form it is there, the more and more you use AI, deep learning, this type of tools for developing solution, one should always keep in mind the energy efficient computing solution, so that to design lightweight security schemes. So these are actually research challenges to reduce energy consumption of secure IoT network, and we move towards a greener IoT ecosystem. So with this, I conclude this session, and I'll take up the next session maybe with a little break. I try to cover up some of the times that we lost because of the delay. Over to you,
Thank you,
Aditi.
sir. Thank you, sir. Thank you for the wonderful session, sir.
So next session is also mine, I suppose.
Yes, sir. Yes, sir. Next session from 11 to 12 is yours.
So can I take a just 2-3 minutes breather? Or
Yes, sir.
Yeah.
Yes, sir. Sure, sir.
11:05 I will start. You just tell me, huh?
Okay, sir.
Okay.
So dear participants, there is one announcement from our end. So we request all the participants to attend the session from the WebEx link, which has been posted in your registered Gmail IDs. YouTube link lecture won't be considered for attendance. Thank you. Hello. Yes, participants, the study materials and the presentations which will be used in this lecture, presented and used in the lecture, will be uploaded in the Google Drive link, which has been shared with. The drive will be updated as the course progresses. So next we will start with lecture number 3. Hello, Ratnajit sir.
Rosa, can we start? Or
Sir, yes, sir, we can start. Sir.
okay, so we start our next topic, which is communication technologies for IoT. And this will be shared by myself and my colleague, Dr. Argadeep. So I will cover the part 1 of it. And mostly I will emphasize on LP1 LoRa based technologies and also talk about the Wi-Fi upcoming technologies. Whereas my colleague, Dr. Argadeep, he will talk mostly on NB-IoT, what we have mentioned, and also about Li-Fi system, the free space light communication based communication, which is coming up. Am I audible clearly?
Yes, sir, you're audible, sir.
Yes,
Okay.
sir.
Thank you. So the technological issues that we need to consider, particularly in designing communication technologies for IoT, is modulation, coding, frequency bands, bandwidth, the range, because you please note that in most of these ISM band communication, there is a cap on the amount of power that you can transmit. Even in cellular frequency bands also, there are cap on the power that you can transmit from a base station or a device. And you want the device to actually send information as long as possible, maintaining this cap on the transmit power. So multiple access technologies like spread spectrum technologies, DSSS, CSS, FHSS, then multi-carrier type technologies like OFDM, OFDMA, SCFDMA, all these issues actually dictate the design of communication devices that are used for IoT. And therefore, let us try to understand. We just gave an overview. We said that there are 3 broad ranges, and for long range, we use either cellular or LP1. Mid range, we use Wi-Fi and other technologies, and short range, maybe Bluetooth and this RFID, so this type of cases. So let us go into a little bit more detail and let us see the technical requirements and how they are actually done. So we start with LP1 technologies, low power wide area network, and the talk of actually 4 C approaches. The capacity should be large, coverage, also the range should be large, cost should be as low as possible, and energy consumption, battery life, latency, those issues are to be taken into account. So taking these things into account, over the past decade, lot of technologies have been developed. So first, let me put a summary of the LP1 technologies that are available. There are two approaches when it goes to LP1 technologies. One is called UNB or ultra narrowband approach. Now here, in this approach, employ an ultra narrowband spectrum. It offers very good link budget due to concentration of power in a narrow frequency band and low in-band receive noise. You know that as the noise picked up by the system actually depends on the bandwidth. It allows the long range coverage with long battery life. But if your information is residing on a very narrow band of frequencies, a small frequency change over time may become comparatively significant with respect to signal bandwidth. So the pluses and minuses we have actually marked. Another generic approach is called spread spectrum, and that means the bandwidth that you use for transmission of the signal is higher than the bandwidth of the message signal. So it spreads data, digital signal over a bandwidth which is much larger than the bandwidth of the message signal, and we talk of spreading spectrum also. Transmit at a lower spectral power density. So since there is a cap already on the amount of available power or transmit power, and if you spread it over a band of frequencies, the spectral power density becomes much lower. At times it is comparable or below noise floor also. So difficult to detect, intercept, demodulate, and jam. So security, some amount of security is already provided at the signal level. And increased bandwidth and complexity power control is required. So we'll look into some of those issues. So emerging proprietary LP1 technologies. So the very popular one is LoRa. It was developed by Semtech, and although LoRa itself is patented technology, LoRa Alliance is an open non-profit association responsible to develop LoRa technology based protocol specification called LoRaWAN, and it is using unlicensed spectrum. Similarly, another upcoming technology is random phase, and it is also proprietary. Random phase multiple access RPMA is a spread spectrum based LP1 technology developed by Ingenu. It uses unlicensed ISM band and offers secure communication. So you can see that LoRa and RPMA, they fall into this category of spread spectrum. As I told, there are two approaches actually. One is going to our ultra narrowband, and or narrowband, another is going towards spread spectrum. The other technologies, Sigfox, it is a UNB based LP1 technology, uses unlicensed spectrum for IoT connectivity and transmits small amount of data. Effective for uplink, not so effective in the downlink communication. And in many times in IoT communication, uplink become, that means from the device to the gateway or to cloud, this becomes more vital, particularly when you are engaging these sensors to do the data collection or gathering of data. Similarly, Telensa is a UNB-based LP1 technology developed by this company, Telensa, and they are specialized in smart street lighting. So little bit going more into the details or technical aspects of all these things, we are comparing the 4 technologies here. You can see that LoRaWAN, Sigfox, and then Ingenu and NB-IoT. NB-IoT is from our utilizing the cellular systems and licensed bandwidth, LTE. So let us look into LoRaWAN, for example. The modulation is CSS, charge spread spectra. I will go into little detail of this LoRa specification. We'll try to see what is CSS and how it is used. If you look at one thing, these are all, if you look at the frequencies, these are all 433 megahertz, 868 megahertz, 915 megahertz, 430 megahertz in different countries. But all are below, these are called sub gigahertz frequencies, below 1 gigahertz. And why it is so? Because when you have frequency, lower frequency, and you are transmitting wirelessly, your range increases. You may recollect that the range or the received power, it decreases as square of the frequency. So it decreases very fast. And for the same transmit power, if you are using higher frequency signal, your range will be less. And that's why these are the problems which are being faced today by, as we try to use millimeter wave frequencies in 5G and all, and a lot of other technologies, other concepts need to come in like beamforming and all to increase the range. But sub gigahertz frequencies, there, since the frequency is less, they travel for a longer duration distance, and also Doppler shift, which also again depends upon the carrier frequency, is also very less. Data rate varies from 0.3 to 37.5 kbps, and at the most 50 kbps, very low data rate. I will see how this data rate is calculated. And then bandwidth 500 to 125 kilohertz. There are other specifications where you have even lower bandwidth. And range, you can see that you can go from 5 to 20 kilometers depending upon the technology. There is provision for forward error control. You know that when we transmit information over the channel, we do some coding. The channel codes are used so that it can provide robustness against the impediment produced by the channel. And you can correct certain number of errors. So these are called forward error correcting codes. The MAC is unslotted Aloha. Aloha protocol, many of us, we are aware of. It is a random access protocol. And you transmit whenever you have data, there will be collision. And then you lose, but because of the broadcast nature of the wireless media, you will come to know that your transmission attempt has not been successful, so you retransmit. So this type of random access protocols are called Aloha, and it is utilized. Topology, usually these are organized as star of star. There can be adaptive data rate, and also encryption is used, advanced encryption standard AES 128B. Sigfox, if you look into, it uses UNB DBPSK at the uplink and Gaussian frequency shift keying, GFSK, in the downlink. It is sub gigahertz, 868 megahertz and 902 megahertz, and then you get bit rates. It also uses unslotted Aloha, and no encryption is supported in this. This Ingenu, they have something called RPMA, again a proprietary scheme, random phase multiple access, which is similar to DSSS and operate at a higher frequency, 2.4 gigahertz. And therefore you can see that immediately the range reduces from LoRa or Sigfox, and they also provide encryption, authentication, and encryption. NB-IoT is licensed LTE bandwidth. It can support much higher data rates and provide range up to 1 to 10 kilometer, what is being supported by these LTE technologies. It uses slotted Aloha. Slotted Aloha is again a random access protocol, but it is synchronized. Transmission is synchronized. You cannot start your transmission anywhere, and that actually increases the efficiency. So if you look at the power, 40 to 30, 14 to 25, 21. So most of these output power transmitted are about 20 dBm. So with very little power, 0 dBm is 1 milliwatt. So with about 20 dBm of power, they provide you a range of 5 to 20 kilometers. You can imagine how efficiently these systems are designed. So this is where actually Sigfox, LoRa, and NB-IoT are compared in terms of these are system design parameters in terms of cost, deployment, coverage, range, scalability, latency. So you can see that NB-IoT has a better latency performance, and in that way LoRa is in between. Payload length, QoS, and battery life, of course, LoRa and Sigfox, they are better performer. As I told that we'll go into some detail of the LoRa or sharp spectrum communication. So a chart is essentially a waveform in which the instantaneous frequency varies as a function of time. So it is like a frequency modulated signal, and depending upon whether the frequency increasing or decreasing, we can have a up chart or a down chart. And you can use this up chart and down chart over a given interval of time for transmitting bits. For example, you may transmit a binary 1 by increasing the frequency from some F1 to F2, and you can transmit a 0 by decreasing that frequency from F2 to F1. Hello, Shobri, I'm in a talk. I will call you later. So let us consider a sharp waveform of unity amplitude and having a duration of t. Then mathematically, you can write st to be equal to cos 2 pi phi t, where phi t and instantaneous frequency is d phi t dt, and sharp rate is defined as the rate of change of instantaneous frequency and usually written as mu t. Now for an up chirp, mu t is greater than 0, and for a down chirp, it is less than 0. And based on the variation of chirp rate, we can categorize this chirp as either linear or non-linear. So if it is a linear chirp, mu will be a constant. So for a linear chirp, mu is constant, and instantaneous frequency for a linear chirp having a bandwidth b is ft is equal to fl plus mu t, and b is equal to fh minus fl. fh is the highest frequency, fl is the lower frequency. And mu can be defined as b by t. Accordingly, a linear upchirp waveform is given by, so if you go back to your cos these things, it is cos 2 pi theta t, and theta t you can actually get by integrating this ft, and integration of this will give you FLT plus half mu t square over the interval 0 to capital T. So this will represent a up sharp waveform, and a down sharp waveform is given by you will get a minus sign here, and for a sharp signal centered at 0, so this is from 0 to T, an up sharp and down sharp waveform we can write in a using a common notation. So SIT is equal to 2 pi f naught t minus 1 raised to the power 1 minus I minus 1 half mu t square from minus t by 2 to t by 2. So you are shifting the time reference, and f naught is the center frequency, and you can put I equal to 1 or 2. So if you put I is equal to 1, then this part will become 1, and you will get actually the up sharp equation what. And if you put I equal to 2, then it will become minus 1, so you will get the down sharp equation. So these are how mathematically a sharp waveform is described, a linear sharp waveform. You can use these waveforms for transmission of data, but we'll see that in LoRa, we just go beyond transmission of bits, we transmit symbols and what are the changes made. So this is the up sharp waveform normalized. So you can see that frequency starts from a low frequency value, and then it becomes very compressed as we move towards the end of the time interval. And the bottom one actually shows how frequency rises from 0 to 1 normalized frequency. Is my screen visible and I am audible?
Yes, sir. Yes, sir. Your screen is also visible and audible.
Thank you, thank you. Keep me informed time to time.
Yes,
Similarly, we have this linear down sharp. You can see that it starts with a higher frequency content and goes towards a lower frequency over time. So these are the sharp signals we use for communication. Sharp spread spectrum, CSS, it is a spread spectrum technique that uses wideband linear frequency modulated sharp pulses to encode information. As with other spread spectrum method, sharp spread spectrum uses the entire allocated bandwidth to broadcast a signal, making it robust to channel noise. Now, why we have gone for CSS? There are many reasons. One is it is robust to channel noise. Sharp spread spectrum is resistant to multipath fading when operating at a very low power. So the fading effect also, it is resistant. Now, how it is resistant, if you need a complete analysis, I think I will not be able to go into the details in this 1 hour. But these are established, these are proven. It does not add any pseudo-random elements. when we go for direct sequence spread spectrum, we multiply the incoming wave with a noise like a sequence of chips, and then spread the spectrum. Here we are not multiplying by this type of chips, rather we are uh, changing the instead rely on the linear nature of the chirp pulse itself. In an analogous manner, the frequency changes from some value, lower value to higher value, or from some higher value to lower value. So it covers the entire band with respect to time, but there is no waveform by which it is multiplied. So it is distinguished from the noise on the channel, instead relying on the linear nature of the chirp pulse. And chirp spectrum is resistant to Doppler effect, which is a typical in mobile radio application. So these are some of the issues which makes actually CSS a suitable candidate for low power, wide area, low power or LP, one type of application as a candidate modulation scheme. So this I have already mentioned. In CSS modulation, the spreading effect is obtained through continuously varying carrier frequency. Now we define a spreading factor SF, and 2 to the power SF is equal to B by RS. RS is the symbol rate, and that can be written as B into T. And in LoRa particularly, this SF can be 7, 8, spreading factor can be 7, 8 up to 12. So it is picked up from this set. And B is the spread bandwidth. This is the bandwidth after spreading. RS is the symbol rate, and T is equal to 1 by RS is the chirp duration. Please note that I have taken a very simple reference where these are explained. There are in recent time, later on I will show some of the publications where complete analysis have been done, very robust analysis have been done. So we are referring to 4 here. I will show you what is that reference. So as we have said that it can be written in the complex form as e to the power j phi t over the interval minus capital T by T to T by T and 0 otherwise. And instantaneous frequency ft can be defined in this case as 1 by 2 pi d phi t dt. I will take you through these two links. So this is a recent paper, IEEE signal processing letter. Is my screen visible?
Yes, it's visible.
So it is IEEE signal processing letter 2017. And here they say that the modulation underlying LoRa is patented and has never been described theoretically. Very recently, this theoretical investigation on the LoRa modulation schemes are coming up. The aim of this letter is to give the first rigorous mathematical signal processing description of the modulation and demodulation process. And LoRa is one of the LP1 and is gaining quite a lot of commercial traction. Strictly speaking, LoRa is the physical layer of LoRaWAN system whose specification is maintained by LoRa Alliance, and the indeed does not provide any, the patent indeed does not provide any detail in terms of equations and signal processing. So that was the problem, that this patent is there for the scheme, but equations and those things are coming up very recently, analysis. And if you have not seen, this is the patent which actually covers LoRa. US patent is 8406275, and this is assignee is Nanoscale Labs, and a communication system include modulator for generating a charge signal aimed at spreading the frequency spectrum of an information signal over a specified spectral bandwidth of communication channel. So that actually protects their this type of technology. However, in recent times, I will show you later, lot of analytical analysis have been done, and in fact BER in different channel conditions have been evaluated theoretically and analytically in very recent times. So that's why we are also trying to understand this mathematical modeling. I will not be able to take you to very great detail, but let us try to understand what is done. So for a linear chart, FLC is FC plus mu b by tt, we have already seen. And the matched receiver for a linear chart is performed by multiplication with a conjugate chart. So you can show that actually in that form e to the power j phi t, if you multiply two up charts or if you multiply two down charts, it will be giving rise to another upchap or downchap. But if you take a conjugate, if you multiply a upchap or with a downchap, and then you will get actually a impulse at twice the frequency, and that is how it can be detected. So it becomes the matched receiver. The basic CSS modulation permits to send 1 bit per chart. So this is what I told at the very beginning. If you consider a basic CSS modulation, then you can transmit 1 bit either by a up chart or by a down chart. A single LoRa chart may code up to SF is equal to 12 bits. So we have seen that spreading factor is 12. To do so, during one chart period, a specific frequency trajectory is defined for each of the 2 to the power SF symbols. So suppose if you take SF is equal to 7, then you will get 2 to the power 7 different symbols. And for each of these symbols, you need to define a chart trajectory. And this is done with k number of shifted charts. I will not be able to go into detail of this. Actually, these frequencies are allowed to increase. The starting point is shifted. It is allowed to increase up to certain frequency level, and then it is folded. So in that way, by changing the starting point of the frequency, you can have individual signals accounted for. This is done by shifting the frequency range based on a symbol value. And each coded chirp is obtained by a cyclic shift of the reference chirp. And also folding is used. So in the normal chirp, as you have seen, it starts from say minus b by 2 at minus t by 2 and it reaches b by 2 at t by 2. Now you shift it and start from a different frequency, it goes to b and then folds and then it starts from another point. So in that way, the shifting and folding takes place. The instantaneous frequency of the coded chirp is given here. So you can see that you can, this is LC is linear chirp and this is FCC is the chirp spectrum or coded chirp if you take. So when t is within this interval minus t by 2 to t k by b, then you get one frequency and k by b to t by 2 you will get another frequency. So this expression can be plotted with t and FCCT, then you will get different waveforms which will actually show how the frequency changes with time. The binary information flow generated from the MAC layer is actually divided into subsequences, each of SF belonging to 7 to 12. The set of SF consecutive symbols bits constitute a symbol, and the number of possible symbol is actually m into SF. And in LoRa context, SF indicates the spreading factor, and RS and RB, they are related by bit rate by spreading factor. And if you remember our earlier relation, then we can now substitute this RS as RB by SF, and then we get the bit rate equation. So RB is the bit rate, SF into B by 2 raised to the power SF. So for example, if your bandwidth B is 7.8 kilohertz and spreading factor is 12, then RB will be 22 bits per second. Whereas if your bandwidth is 500 kilohertz and SF is 7, then you will get 27 kilobit per second. So these degrees of freedom permit the system to adapt the rate and frequency of occupancy of the transmission conditions. Devices operating at the edge of the gateway range are likely to be assigned with a higher SF, whereas closer devices use lower SF. So this is how the LoRa takes into account when the device is operated at the edge of the gateway coverage. Every gateway has a coverage region. So when the device is at the edge, then you assign higher value of SF. Whereas when you are near, you can actually support higher data rates and you can make the system scalable. So these are some of the references I was talking to. The first reference is, of course, this is the first analysis: frequency shift, chirp modulation, LoRa modulation, IEEE signal processing letters I have already shown. Then closed from approximation of LoRa modulation BR performance in 2018, and 2019, the same group interleaved sharp spreading LoRa based modulation. So there they analyze the LoRa modulation to a much greater detail, evaluates its performance in AWGN and different fading channel scenarios, compare it with other spreading schemes. This is the document based which I have described the dedicated network for IoT 5 state of art and challenges. So that is EI endorsed transaction on Internet of Things, European Alliance for Innovation. And similarly, another reference is available which describes the LoRa physical layer principal performance analysis, that is in ICCS. So this constitutes some of the very recent references where LoRa is explored in detail. For medium range solutions, we have Wi-Fi, Li-Fi, Zigbee, Z-Wave, and thread group. Thread Li-Fi will be covered in detail by my colleague, Dr. Argodeep. So here again, we need to consider the modulation, the IEEE standard over which it works, the band of frequencies. Some work in sub-gigahertz, some work strictly in 2.4 gigahertz, 5 gigahertz like Wi-Fi, and Li-Fi, of course, hundreds of terahertz. The data rate may vary from very low data rate to even high data rate, 1 Gbps you can achieve using Li-Fi. Distances or range 10 to 30 meters, 40 meters you can cover. And then the topology in which you organize them either in mesh, star, point to point, and whether there is any encryption is present. So this constitute the comparison of different technologies and availability of technologies. Similarly, for the short range, we have RFID, NFC, and Bluetooth solutions. Once again, you can see that they use different modulation scheme. Like RFID uses a very simple amplitude shift keying, whereas Bluetooth uses adaptive frequency hop spread spectrum. So you hop from one channel to the other, and basic in one of these channels you use GFSK, Gaussian frequency shift keying. So all these technologies, they use at times very simple schemes, and some of these schemes also have been developed suiting to some technologies. I will spend some time. So this is actually the IoT general network architecture if you consider using all these technologies as given in this IoT system overview by Samit Avane in a ITU presentation. We'll consider a little bit about 802.11 WLAN standards. And 802.11 is the basic LAN standard. Then A, which uses OFDM coding scheme. I am just highlighting 802.11b or G, which we use here, is an extension, and 802.b uses only DSSS, direct sequence spread spectrum. 802.11g applies to WLANs and used for transmission over short distances. And then N was the first time wireless standards, Wi-Fi standards, they introduced MIMO 802.11n, and 802.11 SE, it actually higher speed you achieve here. 802.11 SE Web 2, this technology is multi-user MIMO technology support provided. But if you consider all these Wi-Fi technologies or WLAN standards, they were all operating either at 2.4 gigahertz or 5 gigahertz, that means higher ISM bands. It is only recently this standard has come up, 802.11ah. This is also known as Wi-Fi Hello, and it is the below 1 gigahertz, that is 900 megahertz. And it has a range nearly twice that of other Wi-Fi technologies. It is also able to penetrate wall. This is important. Lower frequencies have higher penetration. Higher frequencies, their wavelength is small, even they get scattered very easily. And other barriers considerably better than previous Wi-Fi standards. So in effect, we can use now either LoRa type of technologies or 802.11h type of technologies for designing your LP1 type of IoT networks. The designer will have to spend some time. Lot of technological solutions are available, but what could be the best solution, which is the most cost-effective solution, which is the most energy-efficient solution, depending upon the situation, the designers will have to work. So I think I have reached the end of my time. It is exactly 12 now, just few seconds left. So I will stop here, and if time permits, I can take one or two questions.
Hello, sir. Thank you, sir. Thank you for the talk. So there are some questions in the Q&A section, sir. With your permission, sir, can we read it?
Let me see how many I can answer right at this moment, and otherwise, because we have already reached the end of my time, I think the next session will start immediately, na?
So the next session will start from 12:30. We will have a 30 minutes break in between from 12.
Okay, so let me take one or two. Do you have any specific question hours and answer session in this FDP, or it's along with the session?
So it's along with the session, sir.
Okay, let me see how many I can answer. If I cannot answer certain things, I will get back to you in some other session, maybe. Please.
Okay, sir. So first question is, why IoT is an embedded system?
IoT is not an embedded system. IoT includes IoT. I try to understand, explain it very clearly. And IoT requires many things. Internet of Things, a thing has the sensing capability, it has the processing capability, and then it has the communication capability. So that is the thing. And when you connect many such things over the internet, then it becomes Internet of Things. And they may be deployed over some geographical region, they may be deployed in a building, like that. There may be a single sensor, there may be hundreds of sensors organized in a network. The embedded part here actually is the processing part, the microcontroller, the memory, and all other things. Any other question?
Yes, sir. Sir, next question is from Mr. Anup Kumar Sengupta, sir. He says, what types of networks are used in IoT?
I told about different topologies. Network, actually, we organize in different topologies. Star topology is there, mesh topologies. Mesh means every node is connected to every other node, but that requires a lot of capabilities for these nodes to get connected to each and every other node. We may have a star topology where we have a central node which is connected to other. Then this central node in turn may get connected to another star, center of another star. So we can have star of star. So various network topologies are possible.
Sir, the next question is, how can IoT be related to AI or ML?
This has been answered in the AI and ML. They are algorithms which operate on large pool of data produced by the sensors. So AI ML together along with IoT actually gives a solution which is useful. If you just get data from a sensor, you can actually set a threshold, so you will get very limited information from there, that if it is above this threshold. But if you are getting IoT data, the data sensed by a sensor from different locations and some program is analyzing it, you get much better insight. So IoT itself will generate the data, the sensors, the network will carry it, the intelligence sitting either in the cloud or in some part of the network will analyze it, and it will draw inferences, produce some action. Yeah, any other? I saw some question coming up on leech protocol.
Yes, sir.
So that was proposed in the context of wireless sensor network. So thereafter, it has been modified also. The basic protocol actually do some clustering. It finds out one of the nodes and the other nodes get connected to it. And these elected nodes, they actually serve just like your access point for the other nodes. And then they aggregate the data and send to the nearest AP. These cluster heads are elected based on the amount of energy remaining in them and keeps on changing, so that a node acting as a cluster head does not die immediately. So there are a lot of issues on the basic protocol that was given, and therefore later on it was modified. Ultimately, these protocols try to improve the lifetime of the network, so that all the nodes are available. And wireless sensor network and IoT, Internet of Things, in that way, has many common features, and the algorithms developed there for WSN can be applied here as well.
Thank you, sir. So next question is from Mr. Syed Arif Ali, sir. So he says, please elaborate four type backend connectivity with some example. And is internet connectivity always must for IoT application?
See, ultimately, when you say Internet of Things, a device has an identifier or address. How you reach the device? It has to be a part of the internet, and then only it can do useful things. And therefore, it is said that the proper application of IoT, you need to have parallel development of communication infrastructure. Suppose you are installing a sensor to measure the soil moisture in a remote place in a paddy field. How at what distance you can transmit that data? If you are using a battery powered sensor, it can transmit maybe 100 meters, 10 meters, 50 meters at the most. But then whom it should transmit? So you must have some internet accessible point there which actually picks up that data, and finally through internet it goes to the cloud for analyzing what this reading of your sensor means. So until and unless you have the communication infrastructure present, communication infrastructure plays a very, very vital role. The sensors, communication infrastructures, they provide the support, and then on top of these you develop the other application layers which do lot of data processing, data rendering, presentation. These things, all things are done, built on the premise that you have sensor performing or getting information for you, network bringing it to you for analysis. So therefore, at the back end, it is very, very important. Your health device that you are wearing, if your smartphone cannot send this data, will it be of any use to you? And your smartphone will have to be connected to some, either to some base station or to some Wi-Fi service provider nearby, and then only the data can travel. So underlying communication network is also very, very equally important.
Thank you, sir. Sir, next question is from Mr. Pavan, sir. So he asked tools to implement IoT systems and if we use more sensors in healthcare.
Healthcare, nowadays people has come up with various sensors like online patient monitoring system. There are plenty of projects available. And IoT simulator platforms are also available. Some are free, some are charged. And I think in our hands-on, our instructor, Mr. Koshalendra, will introduce you to some of the tools where you can carry out this IoT simulation. First of all, there are kits nowadays available where one can do the hands-on, or you can also have simulation platform. You can test your algorithms. In fact, I think MATLAB also has some support for IoT. So there are many platforms available. I cannot list them all right at this moment. And I request Mr. Kushalandra to actually introduce, if he's around, Aditi.
Yes, sir. Hands-on sessions will start from tomorrow.
No,
12.
but if he's there in the meeting,
No,
otherwise,
sir. Right now he's not.
and so you please pass this information to him that they should also introduce the participants to the available simulation platforms. Huh?
Okay, sir. Okay, sir. So with this we comes, all the questions are completed, sir. So we request all the participants to have a break. So next lecture will be lecture number 2, which will start from 12:30 onwards, sir.
Next lecture is, I think, lecture 3.
Sir, lecture 2. Sir,
Oh.
lecture 2 on IoT embedded system sensors and components by Dr.
Dr.
Rishi.
Rishi. Yeah, okay. Thank you.
Yes, sir. Thank you, sir. Thank you for joining today and motivating us, and for this wonderful lecture, sir.
Thank you.
So, dear participants, we request you all to have a short 15 minutes break. It's
So I'm disconnecting myself, huh?
okay, sir. Okay, sir. Thank you, sir. Thank you. So it's so dear participants, it's 12:15. So we request you all to have a 15 minutes break. So next session we will start from 12:30 onwards. Thank you. Participants, we request you not to disconnect your system. You can simply turn off your camera and then come back at 12:30. Thank you. Good afternoon, sir. Rishikesh, sir, can you hear us?
Yes, ma'am. Yes. Yes.
Yeah, good afternoon, sir. Sir,
Good
we
afternoon.
will start the session by 12:30, sir.
Yeah, sure. I'm ready, ma'am.
Okay, sir.
Yeah.
So the presenter rights are provided to you. So, sir,
Okay.
before the session starts, can you share one PPT?
Yeah, yeah. I'm sharing.
Thank you, sir.
Ma'am, is the screen visible?
Yes, sir, absolutely, sir. It's clear and visible, sir.
Okay. Thank you.
So then we will start the session by 12:30.
So should I stop sharing now or what?
Yes, sir, you can stop.
Okay. Okay. Thank you.
Hello.
Hello, ma'am. Yes.
Yes, sir. Sir, we will have a short introduction before the lecture begins, sir.
Yeah, sure. Fine.
Yeah. So before the lecture starts, so with your permission, can we start with the introduction, sir?
Yeah, please, ma'am. Please.
Okay. Thank you, sir. So dear participants, welcome you back in this next session. This next session will be taken by our next expert, Dr. Rishikesh Kulkarni, sir. So before we start, we will have a short introduction. Dr. Rishikesh Kulkarni, sir, is working as assistant professor in the Department of Electronics and Electrical Engineering at Indian Institute of Technology, Guwahati since July 2017. He completed his PhD from the School of Photonics at École Polytechnique Fédérale de Lausanne, Switzerland in 2016. His research interests include digital holography, spectral metrology, interferometry, quantitative phase imaging, spectral imaging, and fringe analysis. With this short introduction, I would like to invite Dr. Rishikesh Kulkarni, sir, to please take our next session, which will be on IoT embedded systems, sensors, and components. Over to you, sir.
Okay. Thank you very much, madam, for the introduction. So first, let me share the screen, the PPT. Is the PPT visible, ma'am? Can you please confirm?
Yes, sir, it is absolutely visible, sir.
Okay. Okay. Thank you. So, good afternoon, everyone. Myself, Rishikesh Kulkarni, and today in this session, we will be discussing about the IoT embedded system sensors and components, which is the topic for this FDP on IoT and applications for smart systems. My area of research is basically falls under sensors part. Okay. So since sensors are component of embedded systems which are used in IoT applications, so I will be discussing about some fundamentals related to the embedded systems which are applied for IoT applications, since the embedded systems have been there around for many years now, and since IoT has come into picture in recent years, they have found application in IoT, and we'll look into the particular characteristics of embedded systems, sensors, and components in this session. Yeah. So Internet of Things, IoT, basically has become so popular because of the ubiquity of internet connectivity that we have right in the current era of digitalization. Now, in the case of IoT, what is the basic thing we encounter is the interaction between physical and digital world, and this interaction occurs over connected network. In this context of IoT, it is over internet, right? And since we are all connected to internet almost all the time through various devices, the popularity of IoT has improved because we could connect the digital world with the physical world over the internet. And then what are those things which are been connected? Now in this talk, we'll be discussing about the things part of the IoT. Okay, which are the things that has been connected? That means the physical parts. So objects that are equipped with sensors, actuators, processors that communicate with each other. And why this communication is occurring over internet is to serve a meaningful purpose. So for that matter, IoT can be considered, like a simple definition of that can be considered as that the pervasive presence of variety of devices. Now, which are those devices, or in these things, in this context, things are sensors, actuator, and mobile phones through unique addressing schemes, and are able to interact and cooperate with each other to reach common goal. Now, this common goal can be different application. We'll look into that in the next slide. So this is the basic purpose of IoT. And in this session, we'll be focusing on the things part of IoT. Now, in this small figure, as you can see, that in 2003, the number of things that were connected to internet is shown with the blue color here, and the number of people on earth is shown with brown color. And certainly at that time, the number of people were much large in number in comparison to the number of things that were connected to internet. However, if you look at 2020, the number of things have already surpassed, and it will certainly surpass, or it will certainly increase in future based on the availability of these things for the connection to internet, right? So you can now visualize the growth IoT has experienced over the years. Now, what are the different opportunities? Instead of application, we can look at it as opportunities which IoT can look into in different domains of application. So right from transportation and mobility, as you can see in automotive electronics, now almost all the automotive components are been equipped with so much of electronics that the new models which are coming up are basically sold based on the features which are provided, which are electronic in nature, right? So right from airbag control system to engine control system and navigation system, like air conditioning and all are basically controlled by electronics. Now, IoT can play a part in that, because you might have seen some recent cars where it is explicitly written on the car that internet inside, right? So this is the way the future automotive industry is going to come up. So they will always be connected to internet, and in a way, all the sensors will also be connected to internet, so that the automotive monitoring can be done over internet. Apart from that, avionics also nowadays, you might have seen that many aeroplanes are basically running in an autopilot mode, wherein the flight control and information system which is being received from the system is utilized for controlling the flight. So there also IoT will find application. Again, apart from these, the road and air traffic. Apart from that, we have railways also. In fact, recently we basically worked on one of the part where the railway monitoring is being currently conducted by the fiber optics, which is laid near the railway tracks. Right? So in some European countries, it has already been in place that you can monitor all the activities related to railway using the fiber optic. And then in maritime engineering, then recently you might have seen in some news articles that e-scooters are basically the new concept, and there also IoT will play a significant role in future. And then apart from the automotive industry or transportation, you have mechanical engineering, wherein the concept where basically took its birth in industry 4.0, wherein the purpose was for factory automation, right? So all the components which are there in the manufacturing plant are able to now communicate with each other in order to come up a product at in a lesser time, at a lesser cost, and possibly in a customized fashion. Right? So in that is the way this industry 4.0 is going ahead. And then we have power engineering and smart grid, because all of these will require energy. Energy management also will be basically handled over internet. And then civil engineering and all number of applications are there. Probably in a few subsequent lectures, you will be dealing with them separately. Like I think in the next class, we have this IoT applied for farming sector, that is agriculture engineering, health monitoring and all. So all these things are there. So the application areas are huge. So opportunities are significant in this domain. But what are the different challenges associated with IoT? That also we need to look at. Based on that, the subsequent component design and all will come into picture. So in the case of challenges, the first thing is the dependability one can have on the different components associated with IoT. That means it should provide an intended service with high probability and should not cause any harm, because you see in these applications, since all the sensors and all are connected to internet. Am I not audible? Hello?
Yes, sir, you're audible, sir.
Yeah, because someone just pinged that I'm not audible.
Yeah,
So,
you're audible.
yeah, okay. So, so the purpose of for obtaining a dependable system is to provide an intended service with high probability. Means the downtime should be small. So and then it should not also cause any harm, because we will be wearing these devices throughout the day, right? So it should not cause any harm, and making the system dependable must not be an afterthought. What does it mean? This statement means is that usually in the design process of IoT, let's say embedded system, sensors and all, the basic focus is on the functionality part of that. That means whether are we achieving the functional specification correctly or not. But the dependability aspect is not taken into consideration. But if you don't do that and probably keep it for the later development, then if it is not dependable, you have to start the design from scratch. That is why making a system dependable should not be an afterthought. It should come into picture right from the design process, start of the design process. Then we have to look into the security aspect also, because IoT basically is going to generate huge amount of data. Now, how are we going to preserve the confidentiality of the data, integrity and availability of the information, especially in the case of health monitoring and all? So this also plays a significant role, and communication also. Then confidentiality we just seen. Then safety of the components, because as I mentioned, we'll be wearing them possibly all the time, like our mobile phone. And then reliability, repairability means repairability in a sense that if because these are physical devices, they may get damaged or degraded over time. So how fast we can repair them, and based on that, availability will be affected. That means if the system is down, how fast you can bring it in a operating condition. So all these factors are going to be important challenges associated with IoT. Now, many times in the case of a design of IoT, we model a physical system with some simulation models, right? But there always exists some mismatch between these two. The reason being, simulation are usually conducted with computer, which is digital in nature, whereas physical nature is mostly analog, right? So there are some constraint, real-time constraint, which will come into picture because the computation will take some time, and this real-time operation will certainly get affected by that. Then hybrid system means, as I mentioned, physical system is analog in nature. The operation you are doing in over internet is in digital in nature. So hybrid systems are important in that context. And then adaptive sampling. It has been observed that we have seen in our basic engineering that the sampling theorem and all. So the sampling are usually done in periodic manner, but it has been observed that it is not very efficient way of sampling. So one has to look into the adaptive sampling approach. So that is which is going to come up and will be a challenge in implementation of IoT. Apart from that, Boolean verification will be replaced by fuzzy verification. What does it mean is that when, let's say in a factory, you are manufacturing a product, if the product is meeting a requirement or not, if that decision is to be taken, that will be given as yes or no, but that will be a Boolean verification. However, if those specifications are, since these specifications have some tolerances, right? So based on that, when we have to do some decision, then Boolean verification will be replaced with fuzzy verification. Apart from that, the very important challenge associated with IoT is energy, because most of the components which will be connected over internet are either powered externally, that means wirelessly, or the battery which is associated with that is of not that high capacity, right? So power is considered as the most important constraint in the embedded system in the case of IoT. Now, if you look at this table, we have three different type of powers requirement depending on the application. Like in factory, let's say for your desktop, take as an example your desktop, it is always connected, that is, it is always plugged to a power system. So in that case, if you look at the other example, that is laptop, which is charged, means we charge the battery and the laptop is running on that. And then there are some devices which are unplugged and there is no battery also available. So for example, sensor network, which will derive the power from the control unit itself, right? Now, when you look at these three different aspects of the objects apart based on the energy requirement, and these are the metrics based on which we are going to decide the energy requirement, that whether the component is going to cause the global warming, because since the number are increasing, this is going to be an important aspect to consider. Then cost of energy also, increased performance, unplugged uptime. So all these things. So if you look at the first example of global warming, sensor network, since it is not always on during its operation, it is supplied power from the other unit, it is not going to affect much because there will be less energy consumption by this and energy dissipation. On the other hand, here, if you look at where the systems which are always connected are going to cause significant global warming, right? And the energy is a very scarce resource, especially in the case of sensor network, because there will be thousands of sensors which will be connected, right? So energy will be very scarce in availability. Then runtime. So in the implementation of embedded system, we should always have full exploitation of available hardware architecture. That means because thousands of them will be utilized, and that is going to increase the cost accordingly. The full exploitation of the hardware must be considered. That means all the available resources must be utilized for during the runtime. Then we'll consider the code size aspect later on. The cost also, so minimum amount of resources should be used in implementing required functionality. That is a very important challenge in the context of IoT. Remember, when we are talking about IoT, we are connecting hundreds of such components together. So it is very important that minimum resources are used. And then mapping of specification to custom hardware. So once all these sensors and all, as we mentioned previously, they are targeting one application, right? So that application will give the specification for each component, and those specifications must be mapped to the custom hardware of embedded system. Okay, and the good compromise must be met between efficiency and flexibility. So this topic we'll discuss when we discuss ASIC processors. And then heterogeneous hardware and software components from various providers. Remember, when we connect hundreds of these components together, they will not be coming from same manufacturer, right? So different manufacturers will have their different specifications and all. So in that case, we'll have heterogeneous hardware. It is not homogeneous, not from the same company. So there will be a compatibility issue, right? And even software. So software development may be done at using different tools. So even there we need to bring in the compatibility to build the IoT system. So these are very important challenges in the case of IoT. So in this, as I mentioned previously, that in this discussion, we are focusing on the physical layer of the IoT, which consists of basically three layers: physical layer, network layer, and application layer, right? So physical layer is the one where we are going to collect the data. Network layer, which does the manipulation of the data to transmit it over the network. And then application area is the one where this data is processed or it is analyzed, right? So one of the simple example is given here. So there is a sensor which is sensing the temperature based on the surrounding, and then it is going to send the signal to the control center. Now this portion, control center, this sending comes under network, and then control action is taken, and then the application will turn on the actuator, which is nothing but a sprinkler in this case, which turns on, and then puts off the flame. And this flame is basically causing the increasing temperature, right? So in this topic, we are going to consider on the sensor part and some part of the control part, that is embedded system. Okay. So what is embedded system? So it is a system consisting of a set of hardware components embedding a software application for performing specific task according to fixed set of rules. Now, when we say specific task, so that is what it is different from your computer, because our computer is not designed for a specific task. Based on different application, installed application, we can run different tasks, but it is not the case with embedded system. In the design process itself, it is designed for performing specific tasks. So the computer scientist Marilyn Wolf basically defined an embedded system as any sort of device which includes a programmable computer, but in itself is not intended to be general purpose computer. As I mentioned, the day-to-day life computer which we use are general purpose, but embedded system you can consider it as a computer, but not for general purpose, right? So then what type of operation does a embedded system perform? It performs these operations, that is, it responds, monitors and controls external environment using sensors and actuators. So you can see that in this case, in this example, there is a temperature sensor, right? So it monitors the sensor output, responds to it. How does it respond? By sending the temperature data to the control center, and then the control algorithm is going to take the control action to turn on the sprinkler, right? So of course, not all the application will have the control part over it. For example, if you want to have a temperature sensor in your home to monitor the ambient temperature all the time, you are not going to control the ambient temperature. It is only for monitoring purpose, right? So the thermometer also, which we use, is for monitoring purpose, not for control purpose. So these are the different tasks which an embedded system perform, and it utilizes sensors and actuators to do those tasks. And then the development of embedded system basically consists of the hardware whose characterization must be done, and then timing, memory usage, power consumption, physical failures are the important aspects which are considered in the development of embedded system. So if you look at a simple block diagram, so you can see that there is a sensor, control unit and actuator, which is a basic, you can say, structure of a embedded system. So where do we find these embedded systems? So apart from IoT, as I mentioned, they have been around for a long time. So almost all the domain of electronics, right from automobiles to consumer electronics to biomedical devices, you will find this embedded system. So the embedded system hardware which you are going to talk today is basically, you can see the different components of the embedded hardware. So this is a physical environment. Remember, we saw that we are working in the physical layer of IoT. So it is in contact. This is the device, or this is the component of IoT which is in contact with the physical environment. So the physical environment parameters are sensed by the sensors, are converted by A to D converters and to digital domain, and then these digital signals are processed, and either they're displayed for monitoring purpose or they are converted into analog signals to drive the actuators, because sensor and actuators are analog in nature, right? And the information processing is being performed in digital domain, right? And then we'll also talk about some aspect about energy storage and energy sources associated with embedded system. So the different characteristic of embedded systems are they are application specific, they are resource challenged, means that like your computer, which you always plug to your 230 volt power supply, such power supply will not be available for an embedded system. Plus, your computer has memory in probably in like GB or TB, but that is not the case with embedded system. The memory is also limited. At the same time, it has to perform real-time operation, right? Because it is continuously monitoring. Plus, it should be power efficient. Since it is resource challenged, the power availability is less, so that must be power efficient. And then, since we are manufacturing them in large number, the manufacturing cost should be small, and also the size associated with the sensor. So I will also show some example that how this form factor is playing important role, especially in design of embedded system for IoT applications. So in the next few slides, we'll discuss each of these blocks: sensor, A2D, information processing, D2A, and actuator in detail. So the first part, the one which is in contact with the device, right? So sorry, with the IoT system, that is sensor. So either you can say it is a sensor or transducer. However, you can make a slight difference between them. That sensor is a device which converts one form of energy into another form of energy, or usable energy, you can say. However, transducer is a device which receives an energy from one system and transmit it into another form similar to sensor. However, in the case of transducer, it is mostly in electrical form, because we want everything in electrical form in order to perform some control action over it using digital controllers, right? So most of the sensors nowadays are basically transducers which convert the physical parameter under observation into electrical form. That means, for example, the example of temperature measurement which saw, that the temperature is converted into equivalent voltage or current by the temperature sensor. So the usable output in response to specified input measurement. And what are those input parameters we are measuring? Temperature, pressure, flow, displacement, humidity, pH. You can note down number of such parameters that are required for monitoring and control applications. So in industry, many processes, you need to control temperature, pressure, flow of the fluids in the plant. And then in the case of automotive applications, you need to measure displacement. And then in agriculture, you need to measure humidity, pH level, and all. So so many parameters are there that must be monitored. So this is the device, that is sensor, is the one which is going to do the task in the embedded system. Now, we need to look into the sensor classification also. You can actually classify sensors based on different criteria. The one is based on energy, this one, which is on the first column. On the right hand side, it is based on the principle of operation. Okay. And you can also classify based on the application. Means you can classify sensors as temperature sensor or pressure sensor or flow sensor, like that. Here, I have only mentioned it for the purpose of presentation, that this is based on energy consumption. That is, either it is active or passive. It means that the active sensors are the one which require an external power supply for its operation, whereas passive sensors are the one which operate by themselves. They don't need external power supply. So, but some energy must be required, right, for their operation. So where does this energy come from? The energy basically comes from the system they are measuring. Okay, the system they are measuring. For example, take an example of a thermometer. Thermometer, you don't need a battery to operate the thermometer. I'm talking about the mercury glass thermometer. So, but for its operation, where does it derive the energy from? It derives the energy from the fluid of which you are measuring the temperature, right? So it takes some heat of that as an input, and then the mercury level, the mercury expands into the glass tube, right? So this is the case with passive sensors, whereas active sensors, which require some external power supply for its operation. The other classification is based on the principle that which parameter is being changed in response to these physical parameters. So you will have some temperature sensors made up of metals whose resistance changes with temperature. So those are resistive sensors. Whereas in other cases, in the case of displacement, we look at one example later on, that based on displacement, some inductive property changing, right? So that will become inductive sensor. Similarly, capacitive sensor is also used for pressure and flow measurement. Then you have electromagnetic sensor, piezoelectric effect. So I hope you know what is piezoelectric effect. It is an effect or where the mechanical vibrations to a piezoelectric device will create the voltage fluctuations when you connect the terminals of the opposite terminals of the device, right? So the mechanical energy is converted into electrical energy, and it is other way around also, that if you supply electrical energy, there is mechanical vibrations, which is observed in piezoelectric devices. So those are also used for displacement and pressure measurement. Then there are thermoelectric, photoresistive, means the photoresistive sensors are the one whose resistance changes depending on the light intensity. So those are photoresistive sensors. So like that. So depending on the working principle, you have this classification. So in the case of a modern sensor technology, you are having number of some sensors connected together in the form of a network. So you might have also read about the sensor network, which is used in the industry. Like thousands of sensors are connected, right? So measuring number of such parameters. So if you look at few examples, like acceleration sensor, which is used in automotive industry, which is manufactured using micro system technology, which has 6 degrees of freedom. That means it is able to measure the acceleration along X direction, Y direction, and Z direction. Also, it is able to measure the orientation, right? So where they are used in aeroplanes, cars, and robots at all these applications. Whereas you have image sensors. As I mentioned, these photoresistive sensors. Similarly, you have image sensors, which are typically your camera, which you use, digital camera or your mobile camera, falls under these image sensors. So there are two basic technologies based on which these image sensors are manufactured. One is charged coupled device, and one is CMOS sensors. But nowadays, CMOS sensors are basically are replacing CCDs in many applications. The reason being that since these sensors are manufactured with CMOS technology, you can incorporate the electronics at the sensor itself. So the processing can be done at the sensor side itself. So that reduces the cost size. That's why your mobile phones, all the cameras are of CMOS type. They are CMOS sensors. Then you have biometric sensors, especially for authentication purpose. Probably almost all countries are going for the biometric recording, right, of people. So for that, you have biometric authentication, including iris scans, fingerprint sensor. Remember, this data also, in one way or the other, is going to be part of IoT, right? So these different sensors are there, which are part of this section of the entire system, right? Then artificial eyes, RFID, you must have already used in many applications, which basically based on the response of a tag to radio frequency signals, right? So almost all of our iCards like are of RFID type. Then automotive sensors. So apart from this, you have rain sensor, tire pressure sensor, collision. Remember, all these I'm talking about can be classified into one of these types. I have mentioned only few, but you can classify them in one of these types. So these are some practical examples, the pictures from the manufacturers for different sensors. So this is resistive sensor. So for what all application one can use that? So you see this example, it's shown of a potentiometer. So we know that potentiometer has 3 arms. So you have a potentiometer, and you can see that this is a moving arm of the potentiometer, right? So it is used for displacement sensor, where the displacement is applied to the moving arm, and this resistance is measured. This delta R is measured now you can see that the displacement D is converted to change in the resistance, right? This is a working principle of potentiometer displacement sensor. That's why you can see different, the shafts are provided to apply the displacement. And you can see the wires which take out the connections to these terminals, which will measure the change in the resistance in function of displacement. Whereas resistive sensors are also designed for strain gauges, especially these are very much popular in mechanical and civil engineering, where you can see this is a metal strip. Basically, it is pasted on the object who's under stress. So whatever strain is developed in the surface, basically it will change the dimension of the metallic strip here, and it is going to change the resistance, right? So it is used for strain measurement, whereas this is a RTD, temperature sensor. So temperature dependent resistor sensor. So which is basically most of the time it is platinum, which is used here. So the resistance changes with temperature linearly mostly for this device. So if you can measure the resistance by putting this bar into the system of which you want to measure the temperature, you will be able to measure it in terms of resistance. So you see same operating principle, but used for different applications. Right? Similarly, you have inductive sensors. So as you can see, you have the two coils here which are shown, and it is a core. It is a movable core which is moving inside the hollow pipe. You can see, and the two coils are wound on this. So here in the middle coil, you supply the AC voltage. So this is a supply voltage, right? And it will couple the magnetic field to both the coils, and it will generate the voltage in these two. When the core is at the center, the voltage generated in these two coils is same. That is V1 and V2, right? And they are connected in series opposition manner. So this voltage here will be V1 minus V2. And when it is at the center, since V1 is equal to V2, output voltage is 0. But the moment you apply the displacement to this, the inside movable core position changes, and it will couple more magnetic field to one flux to one coil in comparison to the other. So V1 will not be equal to V2, right? So then it will generate some non-zero voltage, and that voltage is proportional to the displacement. This is a basic working principle of this. It is called as linear variable differential transformer displacement sensor. And how does it look practically? It looks like this. So the displacement is applied here, and you can take out the signal from here. So you have the entire arrangement kept inside this. Whereas inductive flow sensors are also used for flow measurement. Okay, similar principle, just that the magnetic, the fluid which is flowing is going to rotate a rotor, and that is going to change the magnetic field associated with the coil, and that will generate the pulses. That is basic working principle of inductive flow sensor. They are also used for proximity sensors. So in your at different application in factory automation and all. So if you want to open and close the doors or something like that, or any sort of operation which is on off type, so depending on the proximity, right? So inductive proximity sensors are used. Okay, so remember the working principle is again the same, just that the different applications are there. Similarly, apart from inductive, I'm only quoting only few basic resistive, inductive, and capacitive applications, but you can list so many applications for other type of sensors as well. So capacitive can also be used for proximity sensor. You can see that this is the capacitive sensor, right? So it is basically probably measuring the proximity of this lead, which is kept on the box, right? So it is also used as a pressure sensor and for a humidity sensor. Why humidity sensor? Because based on the presence of humidity, we know that the capacitance is given by this formulation, right? So when there are two plates, two plates which are placed such that there is a dielectric medium in between. Then we can have some capacitance associated with that. And this capacitance is given by this formulation where the epsilon represents the permittivity, A represents the area of the plate, and D represents the distance between the plate, right? Now you can either change A, either change D, or either change epsilon, right? So in fact, in the case of a capacitive humidity sensor, basically what changes is this epsilon, right? So because in the with change in air humidity, the permittivity will change. Similarly, in the case of proximity sensor, what changes is D. Okay, or epsilon are A and are constant, and D changes. So you can have any parameter as a variable, other keeping other constant, and you can design a sensor, right? So this is a basic working principle of capacitive sensor. Now, apart in this list of sensors, I have only noted these three, right? But you can find probably application for all type of sensors, working principle of sensors. So then when you are using sensors in the design of an IoT system, you need to look at certain characteristics which are very much important. It's like specifications for a given sensor. One is linearity. Linearity means for a given input, whatever is the output, that means either change in resistance or inductor or capacitor, how linear it is. Okay, that is basically defined by the linearity characteristic of the sensor. And it is always desirable for any sensor to be linear. Why? Because the subsequent signal processing becomes easier if your response is like this, something like this. It is very difficult to calibrate, and subsequent signal processing becomes difficult for that matter. And then also sensitivity, right? Sensitivity is, you can say, slope of this line is sensitivity, isn't it? Slope of this line, that how sensitive is your sensor for a particular application. For some application, you need very highly sensitive. For some, you don't need that sensitive. For example, if you are using a thermometer for body temperature measurement, if it shows, let's say, 34.8 degrees Celsius, and other one shows 34.9 degrees Celsius, you won't bother much, right? Because 0.1 degree may not make much difference to us, right? But in some chemical process, 0.1 degrees Celsius may make much difference, right? So this is where sensitivity characteristic comes into picture and plays an important role. And then dynamic range. What is dynamic range? That the range over which your sensor is capable of providing the readings. Again, taking an example of temperature sensor, if it is not wise to use a RTD whose temperature measurement range is 0 to 100 degrees Celsius for body temperature measurement. Why? We know that our body temperature may not change beyond this range, right? We know that body temperature doesn't change beyond this range. So it will not be correct to use this range, sensor with this range, right? So the dynamic range also plays an important role in the characterizing the sensor. And then repeatability means at one time it is giving this reading, at other time it is giving this reading. So you see, so much difference is there. So if there is no repeatability, or there is another word for this, precision, how precise your instrument is. So that is also very important. Physical size. So I will come to that later in the next slide about the physical size. And then easy amplification and attenuation means whether the output signal can be easily amplified or not. Minimum loading effect. Remember, all the measurement system in the world whichever we use are going to have some loading effect. What does it mean? I will give a very simple example, that let's say I give this circuit as an example, and I want to measure the voltage across these two terminals. Okay, what I will do, I will connect a voltmeter, right? In ideal scenario, we will take the reading as it is. However, please understand that voltmeter is also going to have some resistance, which is not infinite. Ideally, it should be infinite, but it is not. It has some resistance, right? So if you look at this circuit now, due to this resistance, the effective resistance has changed. I have to now consider the resistance as R2 parallel RV, right? And that will going to change the voltage we are measuring. So this is known as loading effect. So your sensor must have minimum loading effect, right? And then it should have signal condition that will come later. Okay. Now, depending on this characteristic, there are some selection criteria. That is, what should be the operating range, what is the sensitivity, what should be the frequency response and resonant frequency. That means whether the input is static or dynamic. Means if the voltmeter I'm using here, and if the supply voltage is AC, right, not DC, and if the voltmeter is not able to respond to the rapid variation of the supply voltage, it is not going to provide the accurate voltage reading, right? So frequency response also plays an important role. Then environmental compatibility. Now you see, let's say you have a sensor which is placed in an environment whose temperature is always greater than 100 degrees Celsius. Okay. Now, the material which is used for sensor manufacturing should withstand this temperature, right? Otherwise, the sensor itself will get damaged, right? So it must, this is very, very key factor, especially nowadays in IoT also, because we want to place the sensor almost everywhere to collect the data. It should withstand that temperature, environment. Means if I manufacture a sensor here in India, it should withstand the low temperature in European conditions also, right? So that compatibility must be provided. Also, accuracy plays an important role, and usage and ruggedness, right? So it should not be that a small handling issue will damage the sensor, right? The sensor should be rugged enough for operating in rough conditions as well. Then electrical parameters like what should be the voltage range and all that will come into picture. And again, of course, very key aspect, that is cost. Again, why cost matters? Because we are not using one or two sensors here. We are going to use thousands of sensors in the IoT system. So if you look at sensor, especially for IoT application, then there are some additional requirement apart from this. So now your sensor should look to go beyond the simple conversion of one physical parameter to other physical parameter, or such as electrical signal. Okay. And what is required here is it should have low cost, it should have small size, and it should be wireless. This is a very important requirement for IoT application, because you will not take wires, hundreds of wires from the control station to the sensor location to supply the power, right? So it must be wireless in nature, and it should provide self-identification and self-validation. Means this falls under smart sensing. This falls under smart sensing, where it is also capable of self-calibrating and self-diagnostics. What does it mean is that over a period, sometimes sensor actually, the characteristic of sensor degrade. Okay, so the calibration is not correct. But what we want is that since thousands of them are there in the factory, I will not go one by one to calibrate each of them, right? So we want the sensor that can be calibrated by themselves. They are self-calibrating in nature. Okay, and before providing the data, they are performing some data processing. So in fact, if you look at this block diagram of smart sensor, this itself is an embedded system. This itself is embedded system. What I mean by that is, along with the sensing unit, you see there is signal conditioning is there. There is A to D conversion. Then there is microcontroller running the application algorithm, communication, local interface memory, all of this. This is actually sensor. Okay, but it is a smart sensor. which in itself is a embedded system. So I must take you back to this diagram. This is a representative diagram. Okay, this is a representative diagram. This entire section, okay, maybe one unit itself. Okay, this, if the sensor is smart, this entire system will be one unit itself. Just that, because each of them is performing different operation. We have considered them in a separate manner. Okay, there is no hard and fast rule that they should be separate units. They can be part of one unit itself, like smart sensor. Okay. Okay. Now, I just mentioned that there should be some signal processing that must be provided before sending it to the control unit. Some manipulation must be done. So again, I mentioned it is in itself is an embedded system, and embedded software is encoded in this application algorithm. Okay. Compensation for environmental disturbance to measurements that cause systematic error. So we were working with one humidity sensor, okay, which was working on the principle of again capacitance, change in capacitance. It was measuring the humidity of the soil, but it is also function of temperature. So that sensor manufacturer, it is a smart sensor basically. So they have provided the temperature sensor also along with humidity sensor. So what the sensor was doing was that it was measuring humidity along with temperature, and it was compensating the effect of temperature in the humidity measurement. So you see, this is very key aspect, compensation of environmental disturbances, right? So let's say you are using a resistance sensor for strain measurement, but we know that resistance also changes with temperature. So we don't know whether the resistance has changed because of strain or temperature. How will you make sure that which is causing the change in resistance? So we may get wrong results, right, or wrong measurement. So for that, this compensation for environmental disturbance is very much key for a smart sensor. How is it done? So you have to understand the physical mechanism. So the manufacturer of the sensor understood that the soil temperature is going to affect the soil humidity. Okay, so there was a physical understanding. Based on that, they incorporated a temperature sensor along with humidity sensor. And then not only understanding is not only important, we have to quantify. Means we have to measure the temperature. We know that humidity depends on temperature. We have to measure the temperature also, and then make sure that there is availability of suitable secondary sensor. So in that humidity sensor, what was the secondary sensor? The temperature sensor was secondary sensor to measure, right? But remember, it may contain multiple of such sensors for as a secondary sensors. And then report by exception. So this is a very interesting thing, especially from IoT perspective. You see, you don't want sensor to be operating all the time. Okay, means let's say you are measuring a temperature of a plant, of plant, let's say, and you just want to know that or make sure that it is not crossing 50 degrees Celsius. Okay, it is not crossing temperature of 50 degrees Celsius. Now it doesn't matter to me whether its temperature is 30, 31, 32 or what. I'm not interested in these readings. So in that case, we want a sensor to report by exception, means it should send the signal only when the temperature crosses 50 degrees Celsius. So why it is important? It will significantly save our energy on the sensor. Okay, so this is very key aspect for smart sensor for IoT. Again, when we talk about IoT, size also matters. So size, weight, power, cost, sensor packaging, and this is being now achieved with the advancement in micro electromechanical systems. So like electronics, mechanical components are also getting miniaturized using MEMS technology, and they are also incorporated with CMOS technology. See, system on chip. What do you mean by system on chip? All these devices are being manufactured on a single chip, right? So This is going to reduce the power requirement as well as weight and the size. And that's why I mentioned here system on chip. So you see, these are the latest sensors, okay, which are there in market, which are especially used for IoT applications. Now, if you look back our previous designs, you see they are quite bulky, right? And they are of different sizes. They are quite bulky, different sizes. But the current IoT sensors, you can see that the packaging is exactly same for all of them. You see, they can measure temperature, humidity, vibration. There are different sensors there, but so many parameters they can measure, like vibration, change in pressure, light, motion, pressure, again battery testing, process loop, current, voltage, all these things. But the packaging is same, you see, and they have provided an antenna also. This is an antenna which is provided for transmitting the signal. Okay, for transmitting the signal to the control station, right? So this is what you will see now, in which these sensors will be replacing the conventional sensor which I showed you before. So we have now talked about sensor. Now let us discuss about the analog to digital part of the entire embedded system. We know that all the sensors are providing the information in the form of analog signal. So I will draw a very simple example for a resistive sensor. So let's say this is my resistive sensor, which is measuring the temperature. Okay. All the resistances values are same. So this voltage, if I measure this, voltage, it will be in some millivolts or so. Okay. So when all the resistances are same, the two nodes are at equal potential, so the voltage is 0. But with temperature, when the resistance changes, there will be a finite voltage difference between the two nodes, and that voltage we have. But that voltage is analog in nature, right? So for the digital control or transmission over digital communication network, we need to convert it into digital form. So that is being performed by analog to digital converter. But before analog to digital conversion, we perform an important operation of sampling. You see, this signal ET is the analog signal, continuously changing with time. But we sample it at different time instances using sampling device. In fact, this is a sample and hold circuit. This is sample and hold circuit. What does it do? It has a transistor or a switch, you can say electronic switch, which is driven by a clock. Okay. And it is going to charge the capacitor to the voltage value corresponding to the analog signal at different time instances, right? So this period is fixed. So this is a sampling period, T. So for each time T, the clock is going to turn on the transistor and going to charge the capacitor. And the capacitor is going to hold that charge till the next clock input. Okay. That's why it is known as sample and hold. Means it is sampling and holding till this point and then coming down, holding this point, coming down, holding like this. You see, this is the output of a sample and hold circuit, which I just drawn. So these vertical lines are only sampled points, but we should hold them, hold that voltage for till one time period, right? Now the next step is performing the analog to, this is analog. Remember, this voltage is still analog, or I must say continuous. It's not a discrete. But what is discrete? Time is discrete. We have discretized the time in the process of sampling, but voltage level discretization is not yet done. That is being done by ADC converter. Now, before going ahead, we should again mention here that when we are performing sampling for the reliable sampling of the analog signal, we must satisfy the sampling criteria, which is given by the Nyquist, which is also called as Nyquist criteria, where if the signal, analog signal ET, has maximum frequency of f, then the sampling frequency should be greater than or equal to 2 times f. Okay, but what is sampling frequency? It is nothing but 1 by t, right? 1 by t. So accordingly, you should calculate that if I know that maximum frequency in the signal is f, I should choose the sampling frequency such that it is twice the value of maximum frequency f. Okay, and if it is not the case, what I mean by that is that if fs is already chosen by the sample and hold circuit, then some anti-aliasing filter is required. What is anti-aliasing filter? It is required because if this criteria is not satisfied, the sample signal is not a correct representation of the underlying analog signal. Okay, and in that case it is called as aliasing. Means the aliasing is caused by failing in satisfying this criteria. Okay, now if the sample and hold circuit is operating at some frequency fs already, then we should cut off the frequencies below fs by 2. We should filter them out. And how do we do that? We use anti-aliasing filter, so that whatever output we get from the sample and hold is not aliased. Okay, so how do we implement this filter, anti-aliasing filter? Because we want this criteria that all frequencies above fs by 2 should be filtered, so we have to use a low pass filter. Now this is the characteristic of a ideal low pass filter. So with respect to frequency, you can see frequencies above fs by 2 are filtered, and frequency below fs by 2 are passed to the sample and hold circuit by the anti-aliasing filter. So these are very important hardware components associated with the part subsequent to sensor. Whatever we are getting from sensor, we should perform this operation. Then once we get the output from sample and hold circuit, we need to convert the analog voltage level to digital voltage level, discrete voltage level. So here, see, here we are getting the output HT from sample and hold circuit. We are giving it to, this is the ADC part. So this is an example of flash type ADC, which consists of comparators, which has two inputs. One is coming from the input signal, which we are comparing or trying to convert to digital, and other input is derived from a fixed voltage reference source. Okay, so you see that these are three different voltage levels which are compared with the input voltage. Okay, which are compared with the input voltage. So you see here an example is shown that if your input voltage is less than 1 by 2 V reference, right? Less than 1 by 2 V reference, then all the outputs are 0, right, of the comparator. What comparator does? If positive terminal is voltage at positive terminal is higher than voltage at negative terminal, it will generate 1. But in all these cases, it is less than the voltage at negative terminal, so output voltage is 0. So it is going to encode. So this encoding is that it will generate a digital output at 0, 0, right? And then when if it is greater than 1 by 2 V reference, okay, and So sorry, it is not 1 by 2. This will be 1 by 4. If it is less than 1 by 4, all are 0. If it is greater than 1 by 4 but less than 1 by 2, it will generate 0, 0, 0, 1. Like that, you can see that the different voltage level, the different range of the voltage is going to generate the digital output, right? So this is the working principle of flash ADC. Similarly, you have other type which is also there, which is known as successive approximation based ADC converter, which has an inbuilt DAC, which we'll discuss later on. Okay, DAC, that is digital to analog converter. So what does it do is that whatever voltage you are supplying, this is the input voltage which you want to convert to digital. It has some control logic, and what it is doing is that depending on the difference between the voltage generated by DAC, it is going to generate the digital output. The digital output is again converted to analog as V minus, and it is compared with this. So what does this loop does is it tries to minimize this voltage epsilon, output voltage epsilon. So when as epsilon is approximately 0, that what does it mean? Then HT is approximately equal to V minus, which that means WT, which is the digital output, is the digital representation of analog voltage HT. Right? This is the working principle of successive approximation. And then you have other types also, like delta sigma, folding type, pipeline type, and all. Okay, so you can look into it. So integrating type, there different types are there, as I just discussed for the purpose of demonstration of flash type and successive approximation type. Now, in the literature, if you look into these different types of A to D converters have different application areas. Okay, so in some application, you want to convert the signal as fast as possible. Okay, so there you need to choose the sensors which have high input bandwidth. For example, flash is the fastest one to operate, but integrating type, they cannot operate at very fast rate, but they have very good resolution. What is resolution? Number of bits. So you see here, to represent the analog signal, I used only 2 bits. Here we use only 4 bits, right? But if you go on increasing the number of bits, 16 bit, 32 bit, that is going to increase the resolution with which you are representing the analog signal. Okay, so that is possible with integrating type, but the cost we pay there is that they are not good at good for rapidly varying and analog inputs. Okay, so again, so that's why depending on application, one has to choose. So if you don't want very fast operation, that means your analog signal is not fastly varying, you can certainly go with integrating type. But in the case where analog input itself is fastly varying, you have to choose flash, or in between you can do the compromise by choosing either successive or delta. Okay, delta sigma. These are very popular. These two are very popular type of ADCs. Now, once we have done analog to digital conversion, then comes the digital processing part. Okay. Now here there are different types of processors which are there. So it is 1 hour is not sufficient to discuss all of them. We are just going to briefly touch upon what all options are available for design of an embedded system for IoT application based on the processor available. Okay, so if you look at the application specific integrated circuit ASICs, they are very good for designing a particular application, and they are energy efficient because we are designing the hardware especially for a particular application, right? So there is no extra component there, but we lack the flexibility there. Once you design for that, for other application, you have to design it again, means design another circuit again. So there is no flexibility provided. And since we are designing it for particular application, they are energy efficient. The cost of designing and manufacturing can be high because we are focusing on a particular application. So the time involved and the cost involved is quite high. So they are there is a lot of design effort which goes into like the like type of tools which are used for ASIC design. They can be quite costly. Apart from that, they are only appropriate for specific circumstances. Means for a particular application, if you are designing, then you should go for ASICs. But we know that embedded systems are basically flexible. We are operating with different type of sensors. So we should have say processors or information processing units which are flexible in nature. So processors should be flexible in nature, and then they should be available off the shelf. What is off the shelf? Commercial off the shelf means that, as I mentioned, ASICs are designed specifically designed for particular application, but we don't want that. We are building a total system with different components. We can't build a specific component for particular application. So we should choose one which are already available, that is off the shelf components. And the processors which we are choosing for IoT application, okay, they should be resource aware. What does it mean? Is that you can't choose a processor which consumes all the power which is provided to the embedded system. There is no power which is available, let's say for ADC, for display, or for DAC. Then it is not of no use, right? So when you are choosing a processor, you should know the energy constraint you have. That is, your processor must be resource aware. And then when you consider the energy efficiency, so if the energy consumption is minimized, then it should be considered as a cost function, because we are actually solving the optimization problem here, right? We are minimizing something. What is the cost we are minimizing? Energy consumption. And energy consumption should be the cost function, not the execution time. Sometimes what we think that doing things faster using a processor means lesser time energy consumption, but that is not always true, because we know that the energy consumed is power into time, right? Power into time. So sometimes we think that a processor, let's say there is a processor which operates at power P1 for time T, okay, for time T1. So energy consumed will be P1 into T1, right? But some other processor, let's say, is doing the task in time T2. So we may wrongly judge that it is going to perform, it is going to consume less power. But if P2 power consumed is higher than that, then it may happen that T2 may be greater than P1 T1, right? Right. So only execution time should not be considered for minimization purpose. So that may be misleading. So what should be minimized? Energy consumption, not the execution time. So minimization of power and energy both are important aspects, and that basically going to affect the design of power supply in because all these components will be supplied by a power by a common power supply. So the design basically depends on the minimization of the power requirement from the processors, because these are the units like our brain are going to consume maximum power, right? So the energy efficiency should be considered at various level of abstraction, from the design of the instruction set down to design of chip manufacturing. As I mentioned previously also, these aspects must be considered not at the end, but from the start of the design itself, okay? And then which type of power we should consider? We should consider dynamic power, which comes because of the switching operation of the clock, right? And there is static power, means there is some power which is continuously consumed. So both must be considered, okay, while minimizing the energy consumption. Now, this is where this parallel execution came into picture, right? We know that we always talk about parallel computing and all. Why does it come into picture? It basically came because of the purpose of solving the energy efficiency. So parallel execution is a mean to derive energy efficient implementation, right? And it is, see, we are now focusing parallel implementation doesn't mean faster, okay? parallel implementation is mainly designed for energy efficiency, not for time reduction. Okay, so there are different ways. Like one is gated clocking, other is power gating. Means gated clocking means in a particular processor, some part of the processor there is a all of them are running at a clock frequency, right? So some portion at particular stage of the operation is cut off from the clock supply. So that is known as gated clock. Whereas in power gating, some portion of the power processor, the power is cut off from there. Okay. In some stage of the application, right? Sometimes not all the components of the processor require power, right? So you cut off some part. So that is known as power gating. So based on that, there are two contrasting approaches. One is known as globally synchronous, locally asynchronous. That is GSLA, globally synchronous, locally asynchronous, and other is globally asynchronous, locally synchronous. Okay, so this the purpose of coming up with these architectures or the type of processor is to achieve the energy efficiency. And then parallel execution, that is dynamic power management and dynamic voltage and frequency scaling. So sometimes, many times, that we consider the supply voltage specification and the clock frequency to be separate entities of specification. But under dynamic voltage and frequency scaling, there is a pair which is defined, always a pair which is defined, and based on the application, there is a switching which occurs from one pair to other. So for one voltage, there is one clock frequency used. For other voltage, there is another clock frequency used, like that. So there is a dynamic voltage and frequency scaling which is performed by the advanced processors currently. The dynamic power management example which is shown here, you see. So they define different states of the processor. Okay, and based on the state of the processor, there is a power management which is done. Means in the ideal situation, the processor, when it's an ideal situation, it consumes 50 milliwatts. Okay, whereas in the case of in the running mode, you see it consumes around 400 milliwatts. Okay, and from idle to run, the transition is made in 10 microseconds. Whereas there is a sleep mode, like even not in idle mode, in a sleep mode, the power consumption is still lower, that is 160 microwatts. Okay, so these are the different states through which a processor goes through. So that's why when you design algorithms, you design state algorithms, right? The state flow diagram we draw, right? From one operation to the other. So during those periods, sometimes the processor is not in active operation. So in that, you can put them in idle mode or sleep mode. So even your computer, you can nowadays put sleep mode. The reason is it consumes very less amount of power, right? So especially for IoT application, these type of processor are highly required, right? Parallel execution, dynamic power management. Then comes the code complexity. Now in computer, when you write the code, you don't worry about what is the size of the code, because your computers are having memory of terabytes or gigabytes. But that is not the case with embedded system processors. The memory area is limited. Why? Because the size which we are working with is much smaller compared to the personal computer, right? So minimizing the code size is very important for embedded systems, especially for system on chip, because memory and the processor are implemented on the same chip. That is not the case with our computer. You have separate hard drive, HDD, and then SSD. They are separate, but that is not the case with embedded systems. So code minimization, size minimization is very important. In fact, you must have studied that standard RISC processors were designed for achieving the speed. Means reduced instruction set computer processor were designed so that we achieve the speed, but not the code size efficiency. Okay, initially came CISC, right? Complex instruction set computer, but this was this was not suitable for achieving high speed. That's why came RISC processor, right? But the earlier design of complex instruction set processors were actually designed for code size efficiency, because in the older time we were more worried about memory. There was less memory. That's why these sets are designed for code size efficiency. But the recent ones, RISC processors, are designed for speed, because later on the demand changed for speed. We wanted things to be done in a faster mode. But they are not designed for code size efficiency. That's why the old-fashioned CISC processors are finding application in new embedded systems. Recent, especially in IoT applications, they are finding applications, especially this cold fire processor, which are based on Motorola older one, 6800 family of CISC processors. So these new processors are basically utilizing the CISC processor, okay, old-fashioned one, to achieve the code size efficiency, not the speed requirement. Okay. Then the code complexity also reduced based on some compression techniques. Okay, so it is basically to reduce the amount of silicon which is utilized for instruction storage. Remember, we are doing all these things on a single chip, let's say in the case of SoC. So we have to think about the area which is utilized for storage purpose of the memory, right, or code. So instruction is stored in a compressed format. Instructions are stored. So if you look at the normal processor, it will look like this. You have a processor, you have a ROM which stores the program memory. You provide the address and instruction is fetched from this, right? But in the latest processor, we utilize these compression techniques. What they do is, you see, the size of the ROM is lesser, but there is an added component, that is decoder. So what it does is, there is a decoder in between the processor and ROM, that the instruction which is provided by the ROM, means in the program, the instruction is stored in a compressed format, and decoder decompresses it and makes it such that it is readable and executable by the microprocessor. So saving ROM and RAM areas is important, because they are more expensive than the processor themselves. Sometimes the ROM and RAM areas, because we are manufacturing them on a same silicon chip, they cost more than the processor itself. So that is the reason why we have to reduce their size and store the compressed instruction instead of the full instruction. So they are encoding technique for instruction and possibly data also. Even data which is stored in RAM usually is also compressed, so that we utilize lesser memory, or there is a lesser code complexity. So for that matter, the secondary instruction set is utilized, especially by ARM processor family. So it is a narrower instruction set, which is also known as thumb instructions, are dynamically converted into ARM instructions while program is decoded. Means when the program is read from the ROM, it is decoded by the microprocessor, and thumb instructions, means those are the secondary set instructions which are narrow in nature, are stored in the ROM locations. Now, what is the disadvantage of this? That you see, you have to design decoder also. So there is a high development cost involved into this. So another approach is using dictionaries, that each instruction pattern is stored only once. And you basically, instead of storing instructions, you basically have a lookup table, and which provides a pointer to the corresponding instruction. Okay, so like a dictionary, even image processing also, you must have studied about dictionaries. It's like that. Now, there are different features associated with processors, which are very important from the perspective of designing, using these processors in IoT system, embedded systems. So DSP processor provide a number of application-oriented features, such as saturating arithmetic. For example, let's say you are adding 2 bits, 4 bits, let's say, and so you see that this addition will go beyond 4 bits. right? There will be a carry bit which will be generated, isn't it? But in the case of limited resource, what is done is that even the result is stored in 4-bit only, and that is known as saturating arithmetic. So the output is saturated. It is showing that it is saturated. So of course, the appropriate action is taken subsequently, but there is no extra memory which is provided for storing the extra bits. Then fixed point arithmetic. So floating point hardware, if you look for floating point hardware, it increases the cost and power consumption of the processor. That's why in market, if you look at 80% of the DSP processors do not include floating point hardware. They basically go for fixed point, even though this may provide like high resolution in the output, but still, if you look at the cost and power consumption, that's why 80% are still fixed point arithmetic hardware based processors are there. Now, due to the importance of signal processing, that these digital signal processors are equipped with many instruction sets. So different instruction sets are there. So I think we don't have enough time to cover this. Okay. Okay. So multimedia and short vector instruction set. So here what is done is they utilize the concept of packed data type. Nowadays, many processors are coming with registers of 64-bit, right? So instead of using 64-bit for storing single data, they are using packed data where 232-bit data types, 464 data bit types, or 8-bit data types can be stored into single 8-bit register. Okay, and that actually speed up the arithmetic operation. So how is it done? So here very long instruction word processors are designed for this purpose. So the Texas 320C6XS family falls under this, which basically satisfy the computational demand for embedded systems, which are increasing, especially for IoT applications. So here, the performance improvement techniques which are used for, let's say, the processor designed for computer are not suitable for embedded systems. The requirements are totally different, right? So for that, explicit parallelism instruction set computers are designed. As I mentioned, this Texas family falls under this. That detection of parallelism is moved from processor to the compiler. Initially, the parallelism which is performed, the operation of parallelism, as I mentioned, for energy efficiency is done at the processor side, but now it is moved to the compiler. So it avoids spending silicon and energy on the detection of parallelism at runtime. So this operation of parallelism, which was implemented in processor, that hardware is taken out. So that silicon is saved and the energy is saved at the runtime from the processor. So for very long instruction word processors, several operation or instruction are encoded in long instruction words. So you see here, so single instruction packet is there. Okay, multiple instructions. Here in this example, 4 instructions are there, and all of them, they are actually operating on different hardware part of the processor at the same time. That is how they achieve the parallelism. So each operation and instruction is encoded in a separate field of instruction packet, like 1, 2, 3, 4, and each field controls certain hardware. Okay, that is how they achieve the parallelism. But this instruction packet is generated by the compiler. Remember, okay, that is how we have reduced the energy consumption at the processor. So since the compiler is providing this instruction packet, it should be aware of the hardware units and their scheduling. Means sometimes compiler are not aware of what is the hardware down the line, right? But since compiler is generating this instruction packet, which is directly operating on the underlying hardware, that knowledge of the hardware is important, and the scheduling is also performed accordingly, should be performed accordingly, right? Then nowadays we also know that multi-core processors are also becoming popular. That if you go ahead with these epic processors or the multimedia short vector type saturating type, fixed point type. Even if you go on doing this, what will happen is you will hit a power wall, means beyond which you will not be able to achieve higher performance without increasing the clock frequency. But we know that increasing clock frequency increases the power consumption. So that is what is known as power wall, that performance increasing single processor hits the power wall. So that means if we fix the power consumption, then we cannot go beyond a particular performance level. For that matter, the increase is achieved by manufacturing multiple processors on a same semiconductor die. So this is one example shown here. On the same semiconductor die, you have processor 1, processor 2, and you see there are different cores associated with each of them. And then multiple processors integrated on the same chip are known as multi-core. So when we also buy computers, we talk about dual core, quad core, like that, right? So the core architecture can also be homogeneous or heterogeneous. Means in the case, you see, each core is the same thing. That means if you design one core, it is simply replica on the other area of the silicon or semiconductor die, right? But in other type of now this is the architecture for Intel Intel processor. This is also for Intel, which is Intel or ARM, I don't remember, but this is having different architecture. You see Cortex A15 and Cortex A7 on a same thing. So it is a heterogeneous multi-core architecture, right? Now, apart from this, we have another type known as reconfigurable logic-based processors, wherein we have seen that ASICs are very expensive because they are specifically designed for a particular application. So if you look for the application, so if you look for the design which can tackle different type of applications, then we have to resort to software, right? Because hardware is fixed, then we have to resort to software. But software-based solutions are too slow and probably too energy consuming. So the in-between solution is reconfigurable logic, which provides a solution if algorithm can be efficiently implemented in custom hardware. You see, in the case of reconfigurable, it is custom hardware, whereas in ASICs, it is fixed hardware, custom hardware, full custom hardware, means only for that specific application it is designed. It can be almost as fast as special purpose hardware, similar to ASICs, but in contrast to special purpose hardware, the performance function can be changed using configuration data. Because once you design ASIC, you cannot change it, right? But it is not the case with reconfigurable logic. So it is used, especially used for fast prototyping. Like, for example, you are designing an algorithm, you will first design it in MATLAB, because directly designing it in C is difficult. Once you know that it is working, then you will go for C. Similarly, for fast prototyping, you can go for reconfigurable logic. Once the functionality is defined and working well, then you can go for ASIC design, right? So low volume application, if the expected market is too small, then it is not good to go for ASICs. So it is better you can use only reconfigurable logic for that, the base processors for that. Real-time system, the timing of reconfigurable logic design is typically high-level parallel processing. In fact, this reconfigurable logic is used in stock market data analysis and different machine learning applications. Okay, so this configuration means to change the hardware, custom hardware, configurable hardware. This information is stored in RAM. Okay, the configurations are stored in RAM. So the best example of such processor is FPGA, field programmable gate array. As the name suggests, it is the most common reconfigurable hardware, and it is programmable in the field. Means after fabrication, if when it is in the board, you can actually program it and change the hardware. That is in the field programmable. Consists of arrays of different processing elements. Probably I will skip that part because you might have done some part of FPGA. So just the thing that we need to understand, apart from ASICs, the advantage FPGA provide is the configurability. which is very much useful in IoT, embedded system for IoT, because we are targeting so many sensors, right? So we can't have only one type of processor, fixed type of processor. We have to have some option for configuration. Now comes now after your processing part comes the communication part. Now in communication, once the signal, I think this part should come later on, but anyway, so let me first discuss about the digital to analog part. Okay, either you can communicate over network, is especially useful, important from IoT, or you can display it using some organic display or LCDs, or the data, or you can convert it to analog for control action. So this is especially for control action, right? So first, now let us discuss that whatever digital data we have got by processing, we'll try to communicate. Now from the communication, the requirement are, we need to, of course, that the condition, the requirement of embedded system is that it should have real-time behavior, and the communication should be, it is expected that it is point-to-point connection. That means it will increase the efficiency of communication. However, it is not always possible to have point-to-point connection, right? Because in thousands of sensors, you can't connect all the sensor to the communication to the control unit using point-to-point based connection, right? So you have to have some common bus type of system over which the communication can occur. So appropriate bandwidth and communication delay should be defined for the given unit of embedded system. And support for event-driven communication. If you remember, I told you, like a sensor which is measuring a temperature. So it should communicate with the control unit only when the temperature is above 50 degrees Celsius. Below that, it should not communicate, right? So it should support event-driven communication. And then it should have security and privacy and safety and robustness. Means while communicating, the data should not get leaked, right? Now in biomedical application, that if you have installed some device on your body for body parameter measurement and communicating, security and privacy plays an important role, right? And then of course robustness, that it should withstand the environmental conditions. Fault tolerance, maintenance, and diagnostic, similar to these are the same requirement of your embedded system, right? Now there is an important aspect about electrical robustness also, because we are sending the signal. Usually we are sending it over single line with respect to the ground, but when you are sending, the environmental noise is picked up by the communicating wires, right? Now of course the communication can occur over wire, over fiber, or wireless, right? In the case of wired communication, we need to think about the electrical robustness, right? So this noise pickup is usually tackled with differential type of signaling, right? So this signal, you see, the device is going to generate two signals over wires which are twisted, and basically they are kind of out of phase signals, you can see, right? And the reason of using this differential output is that whatever noise is there is going to be present in both the wires, right? And the comparator is going to generate only the difference out of them. You see, it is shown here. The input signal is converted into two out of phase signals, and when you subtract them, you get the original signal back. But if there is noise, the comparator is going to subtract the noise, and the noise is same, so the effect of noise is not present. So this is very popular scheme of providing the electrical robustness in communication. And what are the different ways of guaranteeing real-time behavior? So point-to-point communication can have a good real-time behavior, but requires many connections, as I mentioned. So wiring is easier with common and shared buses. So buses, if they are there, then you can have lesser hardware. In fact, this is more preferred over point-to-point communication. And then you have priority-based arbitration, means over bus, if hundreds of sensors are there which are connected over the bus and communicating with the controller. Okay, then at the same time, let's say 10 sensors are trying to communicate, then how are you going to make sure that the information is sent correctly? Because the hardware will be loaded, right? So we have to have some priority based arbitration saying that this sensor S1 should have more priority of sending data compared to sensor S2, like that. Such priority must be defined. But once you define such priority, the problem is that the lowest priority sensor will hardly get any time to send the data. Okay, so this is the basic problem associated with priority based arbitration. So this sensor will starve to send the data. It is called as starving. So it will not get its time at all. All the time the other sensor will override because of their priority. So the other option is time division multiple access, that each partner in the communication is going to get a fixed time slot over which the communication will occur. Of course, the required time period is, since it is limited, it will have some effect on that, but at least all the sensors, all the partners of communication, not only sensors, will have some time for communicating with the central controller, right? And then there are two aspects also which are used in usual communication, that is carrier sense multiple access with collision detection, means that when there are multiple sensors try to access the bus and try to send the data, the system is able to detect this collision of different communication devices and take the appropriate action. And otherwise, there is a scheme known as carrier sense multiple access with collision avoidance, that the system itself is designed that there is no collision which will occur. Okay, and this is basically preferred over collision detection based method. Now, what are different types of such buses are there? So, the sensor and actuator buses are there, probably defined by each manufacturer, but the most common ones are the field buses, such as controller area network. Now, this is used in automotive industry. This is very popular in automotive industry. Controller area network. Time triggered protocol. You see, as the name suggests, it is based on triggering at a particular time. Okay, so this is basically in the airbag control system of the automobiles. They are used for that purpose, for communication. Then FlexRay. This was designed by number of companies coming together. Okay, this is a standard which is now there. FlexRay type of communication bus for communication. Then local internet network, MAP, EIB, different type of communication buses are already there in practice. Then I2C communication. In fact, I basically worked some time back with I2C bus for battery management. For battery management, they use this I2C communication. Now, we only talked about the wired communication, but of course, the recent trend is about wireless communication. So you have different already available communication protocols, such as the Bluetooth, wireless local area network, Zigbee and all, right? So they are also currently being used. Now, apart from this communication, we have other task which is required from embedded system, that is control. So we have seen that how we can utilize the digital data generated after the processor we communicated. Apart from communication, if you want to take some control action, we have to have some D2A converter, that is digital to analog, because the real world is analog, right? We have to convert that digital into analog world. So that is being done by the D2A converters. Now, displays, as I mentioned, can be LCDs or organic displays, and the output can also be electromechanical, like solenoid switches and all, right? Relays and all. You can drive those. So those are electromechanical devices. So in the case of converting digital to analog, you use these digital to analog converters. So you must have already seen such an operation in some basic electronics course, where you can see that this is a digital data, X is a digital data, 4-bit data, and this is basically weighted summing amplifier, right? Nothing but a weighted summing amplifier. So what it is doing is that it is taking the digital data as an input, right, and generating an output which is proportional to the analog version of the digital data, isn't it? So you can say that Y is the weighted combination of the input. So it is X0 into Vref into R1 divided by R8, R into 8, sorry, R8, R into 8, plus X1 into Vref into R1 divided by R into 4, like that, right? It's a weighted combination, and since it is non-inverting amplifier, there is a minus sign here, right? So you can see that the 4 bits is going to decide the voltage level at the output. So digital data is converted into analog. Now here again the function over discrete time domain, because this digital data is being converted into analog, but it is still a discrete in time. It is like this. Right? It is like this because digitally is like that, right? So sequence of voltage levels are generated. But if you want to generate a smooth signal similar to the analog signal which from where this X is obtained, then you have to use zero order hold functionality. Zero order hold functionality. So here you can see it is similar to your, if you remember our discussion on sample and hold circuit. Similarly here, the output should be generated in zero order hold fashion. And then you can see that since the output voltage, although analog in nature, it is not smooth. It is still discrete in time. So if you want to make it continuous in time, you have to perform some interpolation. So this is interpolation. So what does it mean? It is, you see, Ys is the output which you have calculated at time instant Ts. But what about time instances between two sample points? So you have to do some interpolation. So this is the integrating function. This is a sync function which is used for integrating to obtain the continuous signal. Okay. So you see this, can you see this sync function? This is sync function at this time instant, and then this time instant, this is the sync function, which is used for interpolating. And all of them are added together to generate this signal. You see the blue color one is the actual signal. Red color one is the digital output which is generated, and this is the one which is obtained after interpolation. But how do we implement this sync function? Mathematically, you can't do it in computer or microprocessor, right? It is very time consuming. And you see, this runs from minus infinity to infinity, right? You cannot implement it. But in frequency domain, if you look at it, it is easily doable because you see this is a convolution operation. So you can implement it in Fourier domain by multiplication of the signal with Fourier transform of sync function, which comes out to be a low pass filter. Okay, so if you pass the output of this output through a low pass filter, you will get this signal, which is, you can see they are almost the same. Of course, there will be some error which is due to the quantization error during the analog to digital conversion, but still it is a good representation of the actual analog signal. Right? So D2A converters are very much important for converting the digital data into analog domain for control applications. So there are limitations of this DSC. You see, the output depends on the values of this R and R1. So DSC uses array of registers, which is difficult to build because the precision of registers must be excellent. If there is any change in these values of resistances, that is going to change the output, right? So at the same time, the output which is generated is amplified by a power amplifier. And that power amplifier is very power inefficient. Like class A power amplifier we must have studied. So those amplifiers are very power inefficient to drive motors, lamps, and loudspeakers. So, and at the same time, these DACs or these power amplifiers are not easy to integrate with analog circuitry on a digital microcontroller chips, right? So the cost involved is quite high for this integration. So PWM, that is pulse width modulation, is a much popular approach. Rather than using DSC for converting from digital to analog, this is also being explored very much. That PWM signals are generated by comparing a counter against a value stored in a programmable register. So you see, previously we used reference, right, in analog to digital converter. Similar to that, the registers consist of fixed values against which the output of your digital output is compared. Okay, and it generates a PWM signal, and this is pulse width modulation signal, and the output of this is directly driving the analog circuit. You see, so the input provided like this, something like this. So the width here, the width of the pulse is modulated based on the criteria decided by the values in these registers, right? Now, this is still discrete in time, but we are driving a motor with this, right? So what does it do is that the effort required for filtering high frequency, you see, this is square pulses, right? It consists of very high frequencies. So we have to somehow filter it. That is why we use the low pass filter here. But the low pass filtering operation is performed by the motor itself. We don't need a separate low pass filtering. Motor itself does it because it has the mechanical components which like because of the inertia of the motor, that itself act as a low pass filter. So you don't need an extra low pass filtering for this operation. So PWM is much more efficient from that angle. So for example, if you look at the Atmel 32-bit microcontroller, it has 7 PWM output available in that microcontroller. Okay, so of course, the switching frequency and energy consumption also should be taken in consideration because this is also switching operation. I mean, we have seen previously that switching frequency increase in the energy consumption, right? So appropriate selection of PWM frequency also is an important task. Okay, so now we come at the last part of the entire domain of the embedded system, that is the actuators. Means actuators are nothing but these motors, lamps, and all. Okay, so devices which are controlled by microcontroller or computer, which bring the desirable change in the external environment. Right? If you look at the first example which I talked about, temperature control, we drove the sprinkler. Right? Sprinkler in that case is the actuator. Right? So then heating and cooling will be increasing and decreasing temperature. Then light bulb is there, buzzers are there, motors are there, valves are there. All of these are utilized as actuators in. So these, now we have come into analog domain, right? This is analog output. So this is digital, this is digital, this is analog, right? So we have made a round from analog to digital to analog, right? So I think we'll skip this part. We don't have enough time for this. So I would like to, that's why I'm just skipping this part, and I would like to mention some key application, like an application example, especially for IoT and health sensor monitoring, health monitoring. The IoT sensors I'm talking about, of course you will deal with IoT for health monitoring in detail in subsequent classes. So there are multiple sensor platforms which are used like next generation of personalized self-tracking products, which are mix of accelerators and galvanic skin response sensors, temperature sensor, heart rate sensor. All these things are coming up nowadays. So there are many manufacturers nowadays who are manufacturing, like even the sports brand like Nike also coming up with fuel band, then Fitbit, the different names of different products which are available, which are like smartwatches, wrist band sensors, wearable sensor patches. Now these are all providing the key bio parameters associated with the body, which are utilized for diagnosis purpose, continuous monitoring, right? So because especially in current scenario, we should always consider our, like we should always monitor our body parameters very frequently, so that we know the health condition, right? So for that matter, all these things are coming up. So you can see that these are some examples like Pebble Watch. It is interconnected application, notification of calls. Now this is for calls. Now this is self-tracking watch. This is the basis watch. It is able to monitor the heart rate, temperature, your GSR, galvanic skin response sensor. And then Google also coming up with augmented reality smartwatch, and then others are also there. Now you see here wearable sensor. What do you mean by wearable? It is like a part of your body. Monitoring patches. So you can see that stretchable electronic tools for continuous monitoring of vital signs with flexible electronics. So it is shown here. You can twist it because of the flexible electronics. It is like molded with your skin. So wirelessly transmit the information of heart rate, brain activity, body temperature, all these things. Right now, here, if you look at this, these type of sensors are not the conventional sensors, isn't it? So these are specifically designed for IoT applications. So again, this monitor cardiac rhythm and one arrhythmia. So you can, it is wearable, like a band-aid. Right. Again, mobile applications are also coming up. Now, this is a very interesting application where biodegradable ingestible sensor. So you can actually take it, put it inside the stomach. So it is biodegradable, but while during the stomach, it basically transmits the data about the digestive system. Okay, it sends it wirelessly, and it is digestible. So it is not going to affect the body condition. Then there is blood glucose monitoring system. You see, simply prick of the finger is sufficient to calculate the blood glucose, right? So the quantity of measurement is also very less. Then for EEG monitoring, you see the handheld ultrasound is also there. If you have seen the ultrasound machines in hospital, they are quite bulky, right? Now all these data is now connected through internet, right? So you can directly send the scan data to the doctor, and the doctor can probably give suggestions about medication and all, right? So these are very interesting applications. Again, I have only covered for this thing, but of course other applications are also there. I will not go through the details of this. You will anyway, again, I think there is a session on IoT for home automation also, probably. There you will look into the details of that. So to summarize, the embedded systems we have seen are ubiquitous for IoT applications, and they are the main things of IoT, right? So otherwise, all other things are only communication part. So it is an interface between external world and digital world. So microcontroller play a very important role. So choice of the microcontroller and different components like sensors and all is key factor considering the different challenges associated with IoT. That is what we have seen. And this again, sensor and actuator play an important role in interfacing embedded system with external environment. And design of specific sensors and actuators are the need of the hour, especially for IoT application. You can't use the available sensors nowadays, okay, because they are designed for older versions of embedded systems. But for IoT, the new designs are coming up. So with this, I thank you all for your attention. Thank you.
Thank you, sir. Thank you for this wonderful lecture. Sir, there are a couple of questions from the participant side. Sir, if you permit, we can.
Yeah, please.
Okay, so the first question is from Sony, sir. So he says, what is the difference between self-calibration and self-diagnostic?
Yeah. So self-calibration means that you see, I will give an example again of a temperature measurement. Let's say you have a temperature sensor, which is measuring temperature from 0 to 100 degrees Celsius. Okay. And it is a sensor which is providing the voltage in the range of 0 to 5 volts. So 0 volt means 0 degrees Celsius, 5 volt means 100 degrees Celsius, right? So you have this data. Let's say it is a linear sensor. So you can plot a line using regression, you can plot a line and do the calibration. But over time, what happens is the sensor degrades. Okay. So what I expect is at 50 degrees Celsius, it should give me 2.5 volts, but it doesn't give me 2.5 volts. It gives me 2.3 volts, let's say. So what we can say is it has gone out of calibration. Okay. Now, the conventional approach is that a person, or let's say you take the sensor out, you use another sensor for the calibration purpose, which is of higher accuracy, do the calibration again, okay, and then come up with a relationship between output and input, that is voltage versus temperature, come up with an equation, which is a new equation based on the current state of the sensor. But in the self-calibration, what is done is the sensor is, because there is a microcontroller inside, it itself understands that the calibration time has come. So it does the self-calibration with itself. Okay. Self-calibration. But for that, we must understand their secondary sensor is also required. So secondary sensor will provide the required information to the sensor at place, and the sensor will calibrate with respect to the secondary sensor. What is self-diagnosis is that sometimes a sensor failed to work altogether. Means it will start, what you can say, it will stop giving the reading about the temperature. Okay. Means sensor itself has failed. When I say sensor itself has failed, we are talking about smart sensor here, the one which is in contact with the process, but the microcontroller is still working, right? So the microcontroller will actually tell the controller that the sensor has failed. That is known as self-diagnosis. So there will be a data sent to the control center that the sensor at our end has failed, so it needs a replacement, like that. So that is known as self-diagnosis. So this is the difference between self-calibration and self-diagnosis. Is that fine, ma'am?
Yes, sir. Thank you, sir. Sir, the next question is from Pavani, ma'am. She says, is sensor causes harm to environment and human?
Means, yes, sometimes they do, definitely. Sometimes they do. That's why in the design, we must consider about their effect on environment, because they are also semiconductor devices, right? So they do have some effect on environment and humans. Yes. But as I gave you one example, that's why that the sensors which are there, which you have to put it into the stomach, right? So that should be biodegradable. That should not harm the body. Otherwise, what is the purpose? Isn't it? So those which are not harmful, or that's why organic type of materials are now being utilized for these applications for sensing. Yeah. Yes.
Thank you, sir. Thank you for this wonderful session and solving all the queries of the participants. So, dear participants, in case if you have any queries, you can raise your hands. We can unmute you and you can interact with the expert. So there is one question again from Sanjay Sharma sir. So he says that can you suggest any handbook or reference book that contains list of various sensor and actuators currently available in the market?
Okay. There is a recent book from LCBR. What I will do is, ma'am, the PPT I'm anyway going to share, right?
Yes, sir. Yes, sir.
Yeah. So I have already put one book which I have referred for this presentation, which is explicitly targeting embedded system design for IoT. Okay, but in that book, sensor part is not covered. But along with that, I will give some references. There is a recent 2020 book on sensors and actuators. I will share that. Yes.
Okay, sir. Thank you, sir. So there is another one question from the participant. Sabyasachi sir says that what is the power range required for sensor for IoT? Can we self power by piezoelectric material?
Yeah, in fact, let me share the screen again. Actually, because of time, I skipped that part. Can I share the screen again, ma'am?
Yes, sir, you can. You can. You are the presenter. Yes.
So I skipped that part. Yeah. Is the screen visible, ma'am?
Yes, sir. It is clear.
Yeah. So, sir, if you see here, because electrical energy is the one which is utilized for powering these devices. So, for plugged and unplugged devices, we know that the normal power supply is there, but most commonly batteries used for handheld devices. But nowadays, the energy harvesting, or also called as energy scavenging, is also being performed, where different type of sources which are used to power the sensor, like photovoltaic sensors. Then there is, as you mentioned, piezoelectric devices. So because it is a reversible effect, piezoelectric, mechanical vibration can cause electrical signal can cause mechanical vibration. So this principle is also utilized for energy harvesting. Okay, and then there are thermoelectric generators, like thermocouple is a device with which you can design thermopiles, where temperature difference is basically utilized to generate electrical voltage. And then there is kinetic energy one can utilize of an object. And then currently in I think in wireless power transfer, this this technique, ambient electromagnetic radiation, is also being utilized as a source of energy. So definitely we can utilize this. In fact, this will be the, I think, the focus area of IoT, where sensors will be self-powered using one of these techniques. Yes. Hello.
Yes, sir. Yes, sir. Thank you, sir. Thank you for solving the queries. So next query is from another participant. So
Hello.
yes, sir. Yes, sir.
Yes.
The next participant is Meghna Sharma, ma'am. So she is asking that can we use conventional sensors as smart sensors by interfacing with different protocols, or we need to use only smart sensors?
Yeah, it's an interesting question. But if you look at the example which I gave of the pictures which I've shown about conventional sensors and smart sensors, if you look at the size of those, right? This is where the difference comes into picture. That conventional sensors are not designed in the first place to be smart sensor. So the size aspect is not taken into consideration there. That is one thing. Of course, and one more thing is the electronics which will go into that along with the sensing part probably may not be compatible with the conventional sensor at that location, right? So as I mentioned, when we think about smart sensor, it is not simply picking a sensor separately, electronics separately, and actuator separately. It is actually from the design itself, we have to think that they are being built together, right? So when you conceptualize smart sensor, the electronics part comes simultaneously with the sensor. That doesn't occur in the case of conventional sensor. So that is the issue, that the implementation aspect are different from in conventional and smart sensors. Yes.
Thank you, sir. So one of the participant, Dr. V. Bapuji, sir, has raised his hand. So, sir, can I unmute him?
Yeah, please.
Okay, sir. So, Dr. V. Bapuji, sir, are you there? We have unmuted you. You can.
Madam, I am there here. Hello.
Yes, sir. Yeah, in fact, big data analytics is actually IoT is required for big data analysis.
Sure.
Because whatever we discussed today are the devices which are generating the data for data analysis, isn't it? Yeah. So it is the other way around, that data analysis will be will grow with the advent of with the growth of IoT. Yeah.
Thank you, sir. Thank you. Thank you, sir.
Thank you.
Thank you, sir. So the next participant who has raised his hand is R.C. Ramola, sir. So R.C. Ramola, sir, I am unmuting you. You can interact in the session. Hello.
Yes, sir. I have a question related to the health-related data. Because in the critical condition, we need very accuracy in the health-related data. So
Yes,
how
sir.
we can maintain the data related to the particularly in the hospitals and particularly the critical cases?
Sir, can you be, sir, more specific? Like, are you worried about the accuracy part or the security part?
I am worried about accuracy part.
Okay. Huh. Actually, sir, the thing is the advantage of this. You are right that these sensors we need to first. In fact, one point also I mentioned that although these sensors are satisfying the requirement of IoT being small size, consuming less power and all, they must be accurate, especially in health related monitoring activities. So for that, the other question comes in, that of the data analytics. So if you collect huge amount of data, then the calibration can be done using machine learning techniques.
Okay.
So that will certainly improve the accuracy.
Okay,
so
sir.
the better the more the data is, the better the calibration becomes. So even though your sensor is not linear, the big data will help us in proper fitting of the calibration, and then your accuracy can certainly be good in that case. Yeah, so that data will help in improving the accuracy. Yes.
Okay, sir.
Yes.
Thank you, sir.
Thank you.
Thank you, Ramola, sir, for asking the query. Okay. So, sir, with this, we come to an end to all the queries of the participants. So, thank you for joining, accepting our invitation and delivering the talk today, and also solving all the queries of the participants. However, if there are some other queries remaining, sir, can we mail it to you, sir?
Yeah, sure, definitely. Yeah,
okay, sir. Sir, so with this, we come to an end of this day one of this 2 weeks online faculty development program on Internet of Things. So dear participants, there is an announcement from our end. All the participants, those who have the hardware, are requested to please install the OS tomorrow. In order to find out the stepwise details, how to install that OS in your Raspberry Pi board, all the details are provided in the Drive link. So we request all the participants to please go through the important announcement page, go through the day 2 announcement section. In that you will find the link how to install the OS in the Raspberry Pi board. Tomorrow we will require this in order to do the hands-on session 1. So that's it for my end. Thank you, Rishikesh sir, for joining the session.
Thank you, ma'am. Thank you for the invitation. Thank you very much.
Thank you, sir.
Thank you.
So all the principal investigators who are right now joined with us, we also thank them for getting connected with us and motivating us, and also the participants. So dear participants, with this we come to an end. So we request all the participants to please leave the session. The meeting link will be deactivated in another 2 minutes. Thank you all. So dear participants, in case while installing the software, if you're facing any difficulties, you can let us know in the Telegram group. Thank you all.